Hello friends, welcome to my new data structures and algorithm in Java tutorial series video. Friends, in this tutorial we will discuss how to represent a binary tree in Java. So friends, first we will discuss what is a tree data structure. So here you can see that we are given a tree. A tree is a non-linear data structure which is used for storing the data, and it is made up of nodes and edges without having any cycle. So here you can see that we represent a tree through nodes and edges. So here you can see the nodes are connected to other nodes through edges. So friends, tree is basically a non-linear data structure without having any cycle. So you can see that nodes are connected to each other but they never form a cycle. So here if suppose 6 is pointing to 9, so therefore you can see that it will form a cycle. So therefore this representation is not a tree, because in a tree you will find nodes having edges to other nodes but you will never find a cycle. And you can always think of a tree in the form of a hierarchical structure. And also you can see that each node in a tree can point to n number of nodes in a tree. So here you can see the node having data as 1 is pointing to the 3 nodes by data as 2, 9 and 3. So there can be n number of nodes in a tree which can be referred by any node. So usually a tree is a way of representing the hierarchical structure where the parent node is called as root. So whenever we represent a tree, usually the first node, which is the parent of all other nodes, is generally referred as root. And you can see that it has many levels of additional nodes. So friends, in the tree you can see that one is the parent of all the nodes below it, and it's generally referred by the root because this is the root of the tree, and whatever the edges are coming out from this root, it's pointing to the other nodes. And here you can see that this structure can go to many levels. And also a node who is not pointing to any other node is generally called as leaf. So here you can see that node 1 is a parent of 2, 9 and 3. Node 2 is parent of 4 and 5. And node 4 has no childs, therefore this is called as leaf node. Similarly 5 is a leaf node, 6 is a leaf node, 7 is a leaf node, 9 is a leaf node because they don't have any children. Moving ahead. So friends, what is a binary tree? So friends, a binary tree is a special kind of a tree where each node has 0, 1 or 2 children and not more than that. Can have 0 children, 1 children or at max 2 children. So here in the below diagram you can see as root is the parent of all the nodes. It's having 2 children with data 2 and 3. The node 2, which is parent to 4 and 5, has 2 children 4 and 5. And at the last you can see node 4, which is a leaf node, has 0 children. So friends, similarly a node can have 1 children and the other children can point to null. So friends, a binary tree is basically represented by a tree node. So here you can see a tree node consists of 3 things. One is the data part, which actually holds the data. As you can see, the data is like 1, 2, 3, 6, 7, 4, 5. And it is a pointer to the left node and a pointer to the right node. So these pointers are basically of type tree node itself. So here you can see the node having data as 1 is basically a tree node, and whose left is pointing to the node 2 and whose right is pointing to the node 3. So therefore a binary tree having a tree node consists of only 3 things. One is the data part, one is the pointer to the left tree node, and one is the pointer to the right tree node. So basically the way we represent a binary tree in the graphical form is something like this, that it contains the data which you can see here and 2 edges coming out of it. So here you can see this is the left edge and this is the right edge, and we represent this edge through the left and right pointers. Moving ahead. So as we discussed in our previous slide that a binary tree is basically represented internally through a tree node. So friends, the structure of tree node is something like it contains data, it contains pointer to the right tree node and a pointer to the left tree node in an actual tree. And below you can see the Java code for representing a tree node. So it contains the data, and here I have taken this data in the form of integer and which can be any generic type. And it contains a tree node left which actually points to the node which is just left to this particular node, and one tree node right, which actually points to a tree node which is just right to it. And basically it has one constructor which takes in a data part. So whenever we initialize a tree node, we usually pass the data which we want to store into it. So usually when a node tree node is created, so data which we pass into the constructor is stored in the data variable, and left and right at the time of initialization usually points to null, and later on we make them refer to the other tree nodes. Moving ahead, so let's quickly see a demo how we can create a binary tree. So when we initialize a binary tree, the root is actually pointing to null, and this root is also a type of tree node. Now let's say we have created one tree node having data as 1 and whose left and right is both pointing to null, and which is referred by this temporary variable. So let's say we want to insert this temp into the binary tree. So what we do, we simply assign the value of temp to the root. So it looks something like this. So when we insert one tree node, usually root points to that particular node because this is the only node into the tree. Now let's say we create one more node having data as 2 and whose left and right both pointing to null, which is referred by this temporary node. And if we want to insert this node into the tree, we know that root is already pointing to the node having data as 1. So one thing we can do here is we can either point root left to this particular node or root right to this particular node. So either way we can do. So let's say we assign temporary node value to root left. So it would look something like this. So now here you can see this is a binary tree having two nodes where root is pointing to the node having data as 1 and whose left is pointing to a node having data as 2. And here you can also see that root right is pointing to null and left and right of root 2 is pointing to null. Now let's say we want to insert one more node having data as 3. Now here we can insert this node into a binary tree at 3 places. One is at the root's right, and other 2 places are nodes 2 left and right. So basically we can place this node 3 into these 3 places which is pointing to null. So let's say we insert it at root's right. So it would look something like this. So now here you can see root is having data as 1 and whose left and right both are pointing to a node having data as 2 and 3. And suppose we want to insert one more node, then we can insert it at the 4 places now. So those 4 places would be 2's left, 2's right, and 3's left and 3's right, because those 4 positions are pointing to null. So friends, here I have created one class by name binary tree which is having a main method. So let's implement a binary tree into this class. So friends, in our previous slide we discussed that a binary tree consists of a root node which is of type tree node. So first we'll create an instance variable of type tree node and we'll give name to it as root, because this root node will hold all the other nodes of a binary tree. And in order to represent this tree node, we'll create an inner class by name tree node. So private class tree node. So as we discussed in our previous tutorial, that as it is a binary tree, therefore it will have two pointers. One is pointing to the left tree node and another is pointing to the right tree node. So therefore we'll create two pointers of type tree node as left and right. And this tree node, along with holding the left tree node and the right tree node, it will also hold the data. So we are creating an integer type and which will actually store the data. So this can be any generic type, not supposingly of integer type. We can store any data into this tree node. So in this tutorial I am taking the integer data. Moving ahead. Now below we'll also provide one constructor, and this constructor will take in the data part which we want to store. So when we initialize a tree node, we usually store the data into the data variable. So friends, what is a pre-order binary tree traversal? So friends, in order to traverse each and every node of a binary tree, we apply these 3 steps on the each node of a binary tree. So what we do is, we visit that particular node, and then we traverse its left subtree, and then we traverse its right subtree. So here if you take an example of this tree, then we start with the root node and we apply these 3 steps on the root node. So what we do, we first traverse this node, and then we traverse its complete left subtree, and then we traverse its complete right subtree. So once we process this node, we first go to its left subtree, and there we encounter a node having data as 2. So on this node, we again apply these 3 steps, that we visit this node, and then we visit its left subtree, and then we visit its right subtree. So after we process the node having data as 2, we then go to its left subtree, and then we encounter a node having data as 4. So we apply these 3 steps on the node 4. We first visit this node, and then we traverse to its left subtree, and then to its right subtree. So here you can see node 4 has no left subtree and no right subtree. Therefore we are done with the processing of this node, and then we return back to the node having data as 2. So we have processed this node 2, we have processed the node 4. So now in the third step, we visit the right subtree. So we go to the node 5, and then we apply these 3 steps on the node 5. We first visit this node, then we visit its left subtree, and then we visit its right subtree. So as node 5 is having no left subtree and right subtree, therefore we are done with the processing of the node 5. And once we are done with the node 5, then we are sure that we have processed the right subtree of the node 2. So therefore we have processed 2, then 4, and then we have processed 5. So we are done with the left subtree, and then we again go back to the root node 1. And as we have visited the left subtree of that, we now will visit the right subtree for the node 1. So then we go to the right subtree of the node 1, and when we reach to the node 3, we apply these 3 steps now for the node 3. So first we visit this node, and then we visit its left subtree, and then we visit its right subtree. So after processing the node 3, we go to 6 and we apply these 3 steps. We visit this node, we then go to its left subtree and then go to its right subtree. Now as node 6 is having no left subtree and no right subtree, then we are done with the processing of this node. And then we return back to the node 3. So once we return back to the node 3, we have processed its left subtree, and now the step remains to process its right subtree. So when we reach to the node 7, we first process this node, and then we traverse the left subtree of it and the right subtree of it. So as node 7 has no left subtree and no right subtree, therefore we are done with the processing of the node 7. And then we reach to the node 3. And since we already processed this node, then we reach to the node 1. So friends, in pre-order traversal, we first process the node, and then we process its left subtree, and then we process its right subtree, and this we do recursively for each and every node. So let's see the demonstration of pre-order binary tree traversal. So friends, suppose we want to traverse a tree whose root is 9 and whose left is a node having data as 2 and its left is having data as 4, and the right of node having data as 2 is null, and the root 9 also has the right subtree having the data as 3 and whose left and right subtrees are both pointing to null. So let's see the demonstration of this algorithm, that how we can process the nodes of a binary tree in pre-order traversal. So here you can see that below is the algorithm for it, and as we are applying this pre-order traversal to each and every node recursively, so here we know that the method name is pre-order, and inside this method we are again calling this method to process the left and the right subtree. So friends, when we are doing a pre-order traversal, we are calling this method recursively, and in order to understand this method recursively, Here we are maintaining a call stack which has method call, line number and the root. So in the method call we'll just keep the track of the method, that which method is being called, and we'll also keep the information of the root, that which current node is being processed, and we'll come to know about line number when we are demonstrating the algorithm. So let's call the pre-order method and we'll pass the root as 9. So when the execution point comes to pre-order, we know that the call stack will now execute this pre-order method, and we are keeping the track of the root. So currently the root is being pointed by the data as 9. So then we check that whether root is equal to null or not. So friends, why we are providing this condition is because this is considered as our base case, and as we are calling this pre-order method recursively, we need a point to exit this recursion, that when root is equal to null, then we simply return from that method. So currently you can see root is pointing to 9 here, so therefore it's not equal to null. So the condition in if block comes out to be false. And then as we discussed in our previous slide, that first we visit the node and then we visit its left subtree and then we visit its right subtree. So we'll first visit the node and we'll print the data associated with that node. So the output is 9. So we have processed this node. Moving ahead. So now we are calling the pre-order method to traverse the left subtree for this root. So the value we are passing to this pre-order is root left. So currently you see root left is pointing to the node having data as 2. And as we are maintaining this call stack, so when we call this pre-order method, we'll keep the track of this line numbers, so that once we return it back, we know that from which line we need to execute the method. So currently from line 6 we are calling this pre-order, therefore we will keep the track of this line number. So here we have stored the number as 6. And now we will again call pre-order method and will pass the root.left to it, which is nothing but the node 2. So now root will be the node 2. And here pre-order is again called with a root as node 2. So now we are again executing pre-order with a root as 2. So we'll check whether root is equal to null or not. So currently root is not equal to null. So as we discussed in our previous slide, that once we reach to the left subtree, we process this node and then we go to its left subtree and then to its right subtree. So now we are processing the node 2. So the output would be 2 because we are just printing the data part of it. Moving ahead. And now we'll again call pre-order method recursively and then we'll pass root left to it. So currently root is pointing to the node having data as 2 and its left is pointing to the node having data as 4. So as we are calling this pre-order again, we'll keep the track of the line number. So we are placing the line number as 6 because we know that we are leaving this pre-order at line 6 and we are again calling this pre-order. So the point of execution again reaches to pre-order, and this time the root is roots left, so which is 4. So one new root becomes the node having data as 4. And as we are again executing this pre-order, we know that in the call stack this method will be called again, and this time the root is being 4. So we'll again execute this pre-order recursively. We'll first check whether root is equal to null or not. So currently root is pointing to 4, therefore it's not null. And here we'll simply process this node. So the output would be 4. And after we process this node, we know that now we have to traverse its left subtree and then its right subtree. So first we are processing its left subtree. So we are simply calling pre-order again and we are passing roots left. So currently here you can see root left is pointing to null. So therefore we'll now call this pre-order by passing a value null. And as we are leaving this pre-order now here, we'll keep the track of the line number. So we are calling this pre-order again and now the root would be null because we are traversing root left. So currently root is pointing to 4 and its left is pointing to null. So therefore our new root becomes null, and there will be one more method on the stack with the name preorder, and the root would be null. So we'll again execute the preorder method. So we'll check whether root is equal to null. So currently if you see root is equal to null, so we have reached our base case. So this base case will help us in exiting the recursion, and as we know that we are left with no more nodes in the left subtree to traverse, therefore we'll simply return from this method. So when we return, this method gets executed, so it gets removed from the call stack. And now as this method is removed from the call stack, call goes to the preorder method which was executed just before it. So we'll now start executing this preorder, and as we know that we have left this preorder at the line number 6, so we'll now start from the line number 6. And we also know that when we left this preorder method, at that moment the root was 4. So once the call reaches to this preorder, root will be pointing to 4. So friends, here we have first traversed the node 4, then we process its left subtree, and now we'll go to its right subtree. So that thing we'll do recursively. So in the line 7, now we'll simply go to its right subtree. So as root is 4 and as right is pointing to null, therefore we'll call preorder with a null value. And as we are calling this preorder method with a value as null, we are leaving this preorder method. So we'll update the line number, that from line number 7 we have again called this preorder method. So now this preorder will be called with a value of null. So it's nothing but root's right. So one new root becomes root's right. So now root will be pointing to null. And we also know there will be one more method on the stack with a root value of null. Moving ahead. So we'll check whether root is equal to null or not. So currently root is equal to null. Therefore we'll simply return from this method. So this method gets removed from the call stack, and the execution point goes to the method which called it. So now we'll again start executing this preorder method from the line number 7. And we also know that we have left this preorder when the root was pointing to node 4. So we simply traverse to the node 4, and this would become our root. And then we'll start again executing from the line 7. So once we reach the line 8, we know that we are done with the processing of this preorder method, and whose root is 4. So therefore this method will be removed from the stack, and the execution point will go to a method which called this method. So here the execution reaches the preorder for the root node 2, and we also know that we have left this preorder from the line number 6. So we'll start executing from the line number 6. And we also know that when we left this preorder, at that moment root node was 2. So here the root will now point to the node 2. Moving ahead. And from the line 7, we'll now call the preorder and we'll pass the roots right, because we are applying this preorder traversal to each and every node, that we are first traversing the node, then we are processing its left subtree, and then we are processing its right subtree. So as here you can see, we have processed this node 2, and we also processed its left subtree, which is node 4. So now we are left with the processing of the right subtree. So therefore we are again calling this preorder, and we are passing the value of roots right. So here roots right is null. So therefore we again call this preorder method and will pass the null value to it. And as we are leaving this preorder method and we are calling the new preorder method, so we'll just keep the track of the line number. So it signifies that we are leaving this preorder from the line number 7. So here now we are calling preorder with a value as null. So therefore we know that there would be one more method on the call stack whose current root would be null. So therefore now root will point to null, and we'll start executing this preorder method. So then we'll check whether root is equal to null or not. So currently root is equal to null. Therefore we have reached our base case condition and we'll simply return from this method. So when we return from this method will be removed from the call stack and the execution point will now reach to a method which called this method. And as we have reached to this pre-order method, we know that we had left this method from the line number 7. So therefore the execution will start from the line number 7. And we also know that when we left this pre-order method, at that time root was pointing to the node 2. So therefore this root will now point to 2. And then we'll simply start executing this pre-order method. So once we reach the line number 8, so therefore this method will be removed from the stack. And the execution point will reach to a method previous to it. And we also know that we had left this method from the line number 6. Therefore we'll start executing from the line number 6. And we also know that we had left this pre-order method. At that moment root was 9. So therefore now root will reach to 9. So friends, for the root 9 we have processed the left subtree completely. So now it's the time to process the right subtree. So therefore we start the execution from line number 6. And here we know that we will again call pre-order method, and this time we'll pass roots right, which is the node 3. And as we are leaving this pre-order method, we'll keep the track of the line number. So now pre-order will be called with the root pointing to the node 3. And we also know that there will be now one more method on the stack. So now pre-order will start executing with a root having data as 3. So therefore now root will point to the node having data as 3. Moving ahead, we'll check whether root is equal to null or not. So currently root is not equal to null. So therefore we'll simply process this node and then we'll start processing its left subtree and the right subtree. So we'll simply print the data for this root node, which is 3. And then we'll process the left subtree of it. So we are again calling this pre-order method, and this time we are passing roots left. So it's nothing but we are passing roots left, which is null. And as we are leaving this pre-order method, we'll keep the track of the line number, which is 6. So now the execution point reaches to pre-order, and this time the root is null. So therefore root will point to null. And we also know that there will be one more method on the call stack, and the root will be null. So we'll execute pre-order with a root as null. So we'll check whether root is equal to null or not. So currently root is equal to null. So we have reached our base case. So we'll simply return from this method. Now as we return from this method, the pre-order method on the call stack with the root as null will be removed from the call stack. And the execution point will reach to a method which had called this method. So we'll again start executing pre-order method, and we know that we had left this pre-order from the line number 6. Therefore the execution point will start from the line number 6. And we also know that when we had left this pre-order method, at that time root was pointing to 3. So now root will point to 3. Moving ahead, from the line 7, we'll now again call roots right, because we have traversed the left subtree for the root 3. Now we'll process its right subtree. So we'll again call pre-order method and we'll pass roots right, which is null. So when we are leaving this pre-order, we'll keep the track of the line number. So when we call this pre-order method, we had passed roots right, which is null. So therefore for this pre-order, now root will point to null. And we also know that there will be one more method on the call stack with a root as null. So then we'll check whether root is equal to null or not. So currently root is equal to null. Therefore we have reached our base case. So we'll simply return out from this method. So when we return from this method will be removed from the call stack, and the execution point will reach to a method which called this method. So now we will again start executing this pre-order method, and we know that we had left this method from the line number 7. So we'll start from the line number 7, and we also know that when we had left this pre-order method, root was pointing to 3. So therefore root will reach to 3. Moving ahead. Now once you executed all the statements from this pre-order will be removed from the stack, and the execution point will go to a method which called this method. And the point which we have left this pre-order was at line number 7. So therefore the execution point will start from the line number 7. And we also know that at that moment the root was 9. So therefore now the root will point to the 9. And finally we are done with this pre-order. Therefore this method will be removed from the stack. So friends, in this slide we saw the demonstration of how pre-order traversal works. That it first visits the node, and then it recursively calls pre-order to process the left subtree and then to process the right subtree, and this goes on for each and every node. So here you can see the output as 9, 2, 4, 3. So we have visited 9, then we visited 2, then we visited 4, and then we finally visited 3. So friends, here we saw the demonstration of the algorithm. Now let's go to Eclipse and see the working code. So friends, in my previous tutorial, we discussed how to implement a binary tree in Java. So I had created one class, binary tree, and we have implemented the binary tree in Java. So here we had created an instance variable of type tree node, which was actually root, because this root will hold all the nodes of a binary tree. Now here let's write a code for pre-order traversal of a binary tree. So public void, we'll give the method name as pre-order. Now this method, as we know, will take in a root which we saw in the slide. And as we are going to call this pre-order method recursively, we'll first provide a base case. So the base case would be, if root is equal to null, then simply return from this method. And if root is not equal to null, then simply visit the node. So we'll print root.data. And once the processing of node is done, we will again call pre-order method, and we'll pass root left. And in the last line, we'll again call pre-order method, and we'll pass root.right to it. So here, after processing of a node, we are recursively processing the left subtree and the right subtree in a pre-order fashion. So friend, this is the code for pre-ordered binary tree traversal. Now let's test its working in main method. So first we'll create a binary tree which we actually saw in the slide. I had created few nodes. So I'll just remove one of the node, and I give the data which we saw in the slide as 9, 2, 3 and 4. So we also saw that root was pointing to 9, 9 left was second, and 9 right was holding a node having the data as 3. And we also know that node 2 left pointed to node 4, and we'll just simply remove this line. So here we have created a binary tree which we discussed in the slide, where root is pointing to 9, and whose left is pointing to 2, and whose right is pointing to 3, and then again 2's left is pointing to 4. Now after creating this binary tree, let's test the working of this pre-order method. So in the main method, we'll first create the instance of binary tree. and then we'll simply call create binary tree. Now once we call this create binary tree, the binary tree will be created and the root will hold the actual binary tree for us. And then we'll simply call pre-order and we'll pass the root of the binary tree. So when I run this code, so here you can see it printed 9243, which we actually discussed in the slide. So friends, in my previous tutorial, we discussed what is a pre-order binary tree traversal. So in pre-order tree traversal, we perform the 3 steps for each and every node of a binary tree. That we first visit that particular node, and then we visit its left subtree, and then we visit its right subtree. And this we do for each and every node. So in my previous tutorial, we discussed the recursive pre-order binary tree traversal. And in this tutorial, we will discuss iterative pre-order binary tree traversal. We also discussed that we apply these 3 steps to each and every node of a binary tree, that we visit that particular node, and then we visit its left subtree, and then we visit its right subtree. So friends, in my previous tutorial, we used the recursion in order to traverse the binary tree. Now in this tutorial, as we are not using the recursion and we are using the iterative way, therefore we need to use an additional data structure which could hold the information of the nodes. So friends, when we use recursion and we call the method recursively, so it internally used a stack. So in the iterative way, we will use the stack data structure. So friends, below is the algorithm for iterative pre-order traversal of a binary tree. And as we are using the iterative version of this algorithm, we are creating a stack which could hold the additional information for us, so that when we backtrack to a particular node, we can fetch it from the stack easily. And we also know that stack is a LIFO data structure, which means the last in first out. So the node inserted last would be the first node to be removed. And if you want to know more about stack data structures, you can watch my previous tutorial. So in this tutorial, let's take this example that we want to traverse the nodes of this binary tree. So let's see the demonstration of this algorithm step by step. So basically, when we execute this algorithm, we start with the root, and the first step we check is whether root is equal to null or not. So currently you see root is pointing to the node having data as 1, therefore it's not null. And then we'll create a stack which could hold the tree nodes for us. So here you can see we have created one stack. Now this stack will hold the tree nodes for us. So on the first step, we'll simply push the root node. Moving ahead. So friend, as this is the iterative version of the algorithm, we are using a while loop and we are placing a condition that iterate till the stack is empty. So currently you can see stack is not empty because we have pushed one node. Therefore the condition in while block comes out to be true and while loop executes. So in this line, as we know that stack has only one element, so therefore this element will be popped out, and we'll assign this popped node to a temporary node. So it would look something like this. So first the node will be popped out. So as the 3 node with the data as 1 was popped out, now this temp will point to that particular node. Moving ahead. So friends, in pre-order tree traversal, we first process a node, and then we process its left subtree, and then we process its right subtree. So in the first step, we'll simply print this node. So the output would be 1. Moving ahead. So friends, we have processed this node, and now we will process its left subtree and then its right subtree. So in order to do that, we are first putting the right node on the stack, and then we are putting the left node on the stack, because when we pop it out, we'll first pop out the left node and then we'll pop out the right node. And in order to do that, we are first checking that whether temp right is equal to null or not. So currently temp right is not equal to null. Therefore we'll push the node having data as 3 on the stack. So you can see 3 is now on the stack. And then we'll check whether temp left is equal to null or not. So currently temp left is not equal to null. Therefore we'll push the node having data as 2 on the stack. So friends, as stack is a LIFO data structure, it means the node inserted last would be the first one to be removed. And we also know that in pre-order tree traversal, we first visit the node and then we visit the left subtree. So basically in order to traverse the left subtree first, we push the right node on the stack and then we push the left node. Therefore when we pop it out, we'll pop out the node having data as 2. Now we'll again check in the while loop whether stack is empty or not. So currently stack is not empty. Therefore condition in while loop comes out to be true. And then we'll simply pop an element from the stack and we'll assign it to the temporary node. So the node is popped out. So it means now temp will point to the node having data as 2. And in the next step we'll simply print the data for the temporary node. So 2 is printed and hence we have processed this node, and now we want to process its left subtree first and then its right subtree. So on the stack we'll first put the node which is pointed by temp right, and then we'll put the node which is pointed by temp left. We'll check whether temp right is equal to null or not. So currently temp right is pointing to the node having data as 5, therefore it's not null. Therefore we simply push the node having data as 5 on the stack. And then we'll check whether temp left is equal to null or not. So here you can see temp left is pointing to the node having data as 4. Therefore we'll push the node 4 on the stack. And then we'll again execute the while loop and we'll check whether stack is empty or not. So currently stack is not empty. Therefore the while loop executes. And now in the first step we'll simply pop an element which is on the top of the stack. So here we know that 4 is on the top of the stack, so it will be popped out, and now temp will point to the node 4. Moving ahead, and then we'll simply print the data associated with this node, which is 4, and then we'll simply check whether temp right is equal to null or not. So currently temp right is equal to null. Therefore the condition in if block comes out to be false. And then we'll check whether temp left is equal to null or not. So here you can see temp left is also equal to null. Therefore the condition in if block comes out to be false. And then again in while loop we'll check whether stack is empty or not. So currently you see stack has 2 nodes, therefore it's not empty. So the while loop executes. And the first step will simply pop the top element and will assign its value to the temporary node. So currently you see node having data as 5 is the top element. Therefore we'll pop it out, and now the temp will point to the node having data as 5. Moving ahead. Now we'll simply print the data associated with this temporary node, which is 5. Moving ahead. We check whether temp right is equal to null or not. So currently temp right is equal to null. Therefore the condition in if block comes out to be false. We then check whether temp left is equal to null or not. So here you can see temp left is also null. Therefore the condition in if block comes out to be false. And then we'll again execute the while loop with the condition that stack is empty or not. So currently stack has 1 node, therefore it's not empty. So in the first step we'll simply pop an element from the stack and we'll assign its value to the temporary node. So here you can see when we do stack.pop, the node 3 will pop out and then the temp will point to that particular node. So it would look something like this. So now temp is pointing to the node having data as 3. Moving ahead. Now we'll simply print the data associated with this temporary node. So the output we see 3, and then we check whether temp right is equal to null or not. So currently temp right is not equal to null. Therefore the condition in if block comes out to be true. So in the if block we simply push temp right, which is the node 7 on the stack, and then we'll check whether temp left is equal to null or not. So temp left is pointing to 6, which is not null. Therefore the condition in if block comes out to be true. And we'll simply push temp left on the stack, which is 6. And then in while loop we'll again check the condition whether stack is empty or not. So currently stack has 2 elements, therefore it's not empty. So in the first step we'll simply pop an element from the stack. So the top element is a node having data as 6. So this node will be popped out and its value will be assigned to the temp. So currently temp is pointing to the node having data as 3. And after this step temp will point to the node 6 because when we do stack.pop 6 will be popped out. So it would look something like this. So now temp is pointing to 6. We'll simply print its data on the console, which is 6. And then we'll check whether temp right is equal to null or not. So currently temp right is pointing to null. Therefore the condition in if block comes out to be false. And then we'll check whether temp left is equal to null or not. So temp left is equal to null. Therefore the condition in if block comes out to be false. And then in while loop we'll again check whether stack is empty or not. So currently stack is not empty because there is one node. And in the first step we'll simply pop the element from the stack and then assign its value to temp. So when we pop an element from stack, we know that 7 will be popped out. So therefore temp will now point to 7. So it would look something like this. And then we'll simply print the data associated with this node on the console, which is 7. And then we'll check whether temp right is equal to null or not. So currently temp right is equal to null. Therefore condition in if block comes out to be false. And then we'll again check whether temp left is equal to null or not. So temp left is also equal to null. So therefore the condition in if block comes out to be false. And finally we'll check whether stack is empty or not. So currently you see, as we have processed all the nodes of a binary tree, so the stack is empty. Therefore the condition in while block comes out to be false. So friends, using a stack we saw how we can perform pre-order traversal of a binary tree. So here we discussed about the demonstration of the algorithm. Now let's go to Eclipse and see the working code. We also discussed about the recursive pre-order tree traversal. And in this tutorial we will see the iterative version of it. So therefore I'll just comment this code. And below I will create a method as public void pre-order. And in this method we'll write a code which would perform the iterative pre-order tree traversal. So in the first step we'll check whether root is equal to null or not. So if the root is equal to null, so it means there are no nodes into the binary tree. So therefore we'll simply return from the method. And in the first step we'll simply create a stack. So here we will import the stack from java.util package. And as we discussed in slide, we'll just push the root on the stack. And after that we'll provide a while loop. And inside this while loop we'll check whether stack is empty or not. So if the stack is not empty, then the while loop will be executed. And in the first step we'll create a temporary node and we'll pop the element from the stack and we'll assign it to the temporary node. And as we have popped an element from the stack, we'll simply print its data on the console. and in the next step we'll check that whether temp right is equal to null or not. So if temp right is not equal to null, then we'll simply push temp right on the stack, and we will do this step for the temp left as well. So here if temp left is not equal to null, then we'll simply push temp left on the stack. So friend, this is the iterative version of pre-order tree traversal. Now let's test this working on the main method. So in the main method we have created this binary tree, and then we have called create binary tree. So it will create a binary tree with few nodes, which we discussed in our previous tutorial. And the last I will simply call the pre-order method. And when I run this code, so you can see it printed 9243, and it printed the same what we discussed in our previous tutorials when we had called the recursive version of the pre-order tree traversal. So friends, what is in-order binary tree traversal? So here you can see that in-order binary tree traversal has basically 3 steps, and we apply these 3 steps to each and every node of the binary tree. So the basic steps involved in in-order binary tree traversal is we first visit the left subtree for a particular node, and then we visit the node, and after visiting that node we go to its right subtree. And these 3 steps we apply on each and every node of the binary tree. So let's take an example of the below binary tree. Now let's suppose we want to visit each and every node of this binary tree. So we start with the root. So here you can see root is pointing to node 1. Now we apply these 3 steps on the node 1. So here you can see basically the step 2 is involved in the processing of the node which we are currently pointing to. So here before processing the node 1, what we do, we first traverse its left subtree. So here you can see this is the complete left subtree which we want to traverse before we process this node. And after we process this complete left subtree, we then visit this node, and after visiting this node we go to its right subtree. So here when we are at node 1, then before processing this node we go to its left subtree. Now as we go to its left subtree, we encounter the node 2. So when we encounter the node 2, we apply these 3 steps over the node 2, and before processing the node 2, we first traverse its left subtree, then we process the node, and then we go to its right subtree. So here before processing the node 2, we go to its left subtree first. So once we reach the node 4, we apply these 3 steps on the node 4. So before processing the node 4, we traverse to its left subtree, then we process the node, and then we go to its right subtree. So here you can see node 4 has no left subtree, therefore we are done with the processing of the left subtree. And after we are done with the processing of left subtree, we actually visit the node. So the first element we visit is the node 4, and after we are done with the node 4, we go to its right subtree, and we know that node 4 has no right subtree, therefore we are done with the processing of the node 4 completely. So the call returns back to the node 2, and from the node 2 perspective, we have actually visited its complete left subtree. So now is the chance to visit the node 2. So we actually visit a node 2, and then we go to its right subtree. So when we reach to the node 5, we actually apply these 3 steps now on node 5. We traverse its left subtree, then we visit the node, and then we go to its right subtree. So here you can see node 5 has no left subtree, therefore we are done with the processing of the left subtree. So then we process the node 5, and after we process the node 5, we go to its right subtree. And we know that node 5 has no right subtree, therefore we are done with the processing of the node 5. So friends, after the node 5 is processed, the call returns back to the node 1. And from the node 1's perspective, we have completely traversed the left subtree now. So now is the chance to visit the node 1. So we visit the node 1 and then we go to its right subtree. So once we reach to the node 3, we apply these 3 steps over the node 3. So before processing of the node 3, we first go to its left subtree, then we visit the node and then we go to its right subtree. So when we reach to its left subtree, we encounter a node having data as 6. So we apply these 3 steps now over node 6. We visit its left subtree, then we process the node and then we visit the right subtree. So here as node 6 has no left subtree, therefore we are done with the processing of the left subtree. And then we actually visit the node, and after visiting the node we go to its right subtree. And as node 6 has no right subtree, therefore we are done with the processing of the node 6 completely. Then our call goes back to the node 3, and we know that we have completely visited its left subtree. So now we can visit the node 3. So once we visit the node 3, the third step is involved is we go to its right subtree. So as we go to its right subtree, we encounter a node having data as 7. So on this node 7, we now apply these 3 steps. We first visit the left subtree of it, then we visit the node, and then we visit the right subtree. So friend, as we know that node 7 has no left subtree, therefore we are done with the processing of the left subtree for the node 7. And then we actually visit the node 7 and then we go to its right subtree. So here we can see node 7 has no right subtree, therefore we are done with the processing of the node 7. So here we have visited each and every node, and to each and every node we applied these 3 steps. That before processing the node, we actually visited its complete left subtree, then we visited the node and then we went to its right subtree. So friend, these are the steps involved in in-order binary tree traversal. Now let's go ahead and see the demonstration of the algorithm. So friends, let's suppose you want to traverse this binary tree where root is pointing to the node 9, whose left is pointing to node 2, and whose left is pointing to node 4. And node 4 has no left and right subtree, therefore they are pointing to null. Node 2 has no right subtree, therefore is pointing to null. And here node 9 right is pointing to the node 3, which have no left subtree and the right subtree. So friends, below you can see the algorithm for the in-order binary tree traversal. And here you can see the method name is in-order, which takes in a root. And in the method we are actually again calling the in-order method. Therefore these calls are recursive in nature. So in order to understand this recursion, we are using this call stack where we are keeping the information for the current executing method, and we are also keeping the track of the root node which is getting executed in the particular method call, and we are also keeping the track of the line number whose significance we will see once we demonstrate the algorithm. So let's see the demonstration of this algorithm step by step. Now when we call in-order method and we pass the root, so currently you see root is pointing to the node 9. So we know that this method will be part of our call stack. So it would look something like this, that now this method will be part of our call stack and this method will be executed with the root as 9, because currently root is pointing to 9. We move ahead and we check whether root is equal to null or not. So friends, why we are providing this condition, as this is the base case for our recursion, because in the in-order method we are again calling the in-order method recursively. So friends, in order to break this recursion, we need to provide a base case, and if we don't provide this base case, then this method will call each other recursively. So in order to stop this, we are providing this base case. So currently you see root is pointing to the node 9, therefore it's not null. So the condition in if block comes out to be false. So in the first step what we do is, so what we discussed in the slide, that before processing of a node, we will first traverse its left subtree. So we again call the in-order method, and this time we are passing roots left because we want to process the left subtree now. So here you can see root left is the node 2. Therefore this in-order method will call the in-order method again with the root as 2. So friends, here we are leaving this method and now we are entering to this method again. So we'll keep the track of the line number, that at the line 5 we left this method. so that once this method is processed, we again return back to this method and will start executing from the line 5. So therefore we'll keep the information for the line number whenever we leave any particular method. So here we keep the track of the line number, which is 5, that we are leaving this inOrder method at the line 5 and we are calling this inOrder method again with a root 2. So friends, this method will be called again and this time the root will be the node 2. So here now root, instead of pointing to 9, it will point to 2. And we also know that we have left this method inOrder method, so there will be one more method on the stack. So now this inOrder method will start executing with the root as 2. So let's see the working. We'll first check whether root is equal to null or not. So currently root is pointing to the node 2, therefore it's not null. So friends, as we discussed in the slide, before processing any node, we have to process its left subtree first. So in order to visit the node 2, we'll first have to visit its left subtree. So here we again call inOrder method and we pass root's left. So here you can see root is pointing to the node 2 and we will call inOrder method and we'll pass the root.left, which is node 4. And as we are leaving this method, we will keep the track of the line number. So here now inOrder method will start executing with the root as 4. So currently root is pointing to the node 2. So now it will point to node 4. And here you can see there would be one more method coming on the stack. Now this inOrder method will start executing with the root as 4. Moving ahead, we'll check whether root is equal to null or not. So currently root is pointing to the node 4, therefore it's not null. And here before processing the node 4, we have to first process its left subtree. Therefore we are again calling the inOrder method and we are passing root left. So currently root is pointing to the node 4. So now we are calling this inOrder method and we are passing the null value to it. And here we will keep the track of the line number, that as we are leaving this method and we are calling this method, so we are keeping the track of the line number. So friends, now inOrder method will be called again and this time the root will point to null. So here you can see currently root is pointing to 4 and as we discussed that we are going to root's left. So now root will point to null. And we also know that once this method gets start executing, there will be one more method on the call stack. Now here you can see this inOrder method has root as null. Moving ahead, we'll check whether root is equal to null or not. So currently you see root is equal to null. Therefore we have reached our base case, which makes sense because when we encounter a null value, it means there are no nodes to be traversed. So we simply return from this method. And once we return from this method, we know that this method will be removed from the call stack. And the execution point will go to the method which called this method. So now execution point reaches here. So friends, we know that at line 5, we left this method. So we'll start executing from the line 5 itself. So our execution point will now start from the line 5 because we have processed this information earlier. And we also know that when this method was getting executed, root was pointing to 4. So when step of execution reaches here, root will point to 4. Moving ahead. So friends, here you can see for the node 4 we have processed left subtree. Now is the time to process the actual node. So therefore we simply print root's data on the console. So on the output you can see 4 will be printed because root's data is 4. Moving ahead. And we also saw in the slide that after we process the node, we then go to its right subtree. So in order to go its right subtree, we again call the inOrder method and this time we pass root's right. So currently root is pointing to the node 4 and its right is pointing to null. Therefore we'll again call the in-order method and we'll pass a null value to it. And here, as we are leaving this method on the line 7, we'll keep the track of the line number. So now it will be 7. And we also know that once we call this method, so now in-order method will be called again, and this time with roots right, which is null. So friend, currently root is pointing to node 4, and when we call this in-order method with a null value, therefore now root will point to null. And we also know that there will be one more method on this call stack with the root as null. So let's execute this method. In the first step, we'll check whether root is equal to null or not. So currently root is equal to null. Therefore the condition comes out to be true. And we'll simply return from this method. So once we return from this method, we know that this method will be removed from the call stack, and the method which called it, the execution point will go there. So now the execution point reaches to this method. And we also know that we left this method from the line number 7. So therefore the execution point will start from the line 7. And we also know that when we left this method, root was pointing to node 4. So therefore now root will point to node 4 again. And then we'll start executing from the line 7. So when we reach to line 8, we know that we have completely processed this in-order method. So therefore this method will be removed from the call stack, and the call will go to the method which had called this method. So now call will go to this in-order method, and we know that we had left this method from the line number 5. Therefore the execution point will start executing after the line 5. And we also know that when we are executing this in-order method, at that time root was pointing to node 2. So therefore now root will point to the node 2 and will start executing after line 5. So here we can see that before processing the node 2, we have completely visited its left subtree. So now is the time to process the node itself. Therefore we simply print its data on the console. So you can see 2 gets printed on the console. And after we process the node, we know that now we have to go to its right subtree. So we again call in-order method and we pass the root right value, which is null. And we also know that as we are calling this in-order method, we will update the line number here. So now the execution point reaches to this in-order method, and we know that there will be one more method on the call stack with a root as null. So here you can see root is pointing to node 2. So now this root will point to null, and we'll start executing this in-order method. So in the first step, we check whether root is equal to null. So here you can see root is equal to null. Therefore we'll simply return from this method. And we are returning from this method that because we have already processed its right subtree. So once we return from this method, we know that now this in-order method will be removed from the call stack completely. And now the execution point will reach to this in-order method. And we'll now start executing this in-order method from the line number 7. So we'll start executing from the line number 7, and as we know that when we were executing this in-order method, root was pointing to 2. So now root will point to 2, and then we'll simply execute this in-order method. So once we reach to the end of this method, we know that now this method will be removed from the call stack, and the execution point will reach here. So we'll start from the line number 5, and we also know that when we are executing this method, root was pointing to 9. So therefore now root will point to 9, and then we'll simply execute the steps. So friends, here you can see Before we processed node 9, we completely traversed its left subtree, and after we traverse its left subtree completely, now we are visiting the node. So we are simply printing its data on the console. Moving ahead, and once we are done with the process of this node, we have to process its right subtree. So therefore we are again calling inOrder method, and we are passing the value roots right to it. So here you can see roots right is the node 3, and as we are calling this new method, we are updating the line number. So point of execution reaches to the inOrder method with a root as 3. So now root is pointing to 3, and we also know that as this is a new method on the stack, there will be one entry on the call stack. So here now this inOrder method will start executing with a root as 3. So we first check whether root is equal to null or not. So currently root is pointing to 3, therefore it's not null. And then for the root 3, we apply the inOrder traversal again. We first visit its left subtree. So in order to visit its left subtree, we are calling inOrder method, and we are passing root left value to it. So here you can see root left is pointing to null. Therefore we are calling this inOrder method with the value as null. And as we are leaving this method and we are calling this new method, we will update the line number. So then execution point will reach to this inOrder method with a root as null. So we know that there will be one more method on the call stack with a root as null. And now root will point to null. Moving ahead, we check whether root is equal to null or not. So currently root is equal to null. Therefore we'll simply return from this method, and this method will be completely removed from the call stack. And as this method is removed from the call stack, the execution point reaches to this inOrder method, which actually called the inOrder method with a null value. And from which line we have to start? We have to start the execution from the line number 5. And we also know that when we were executing this inOrder method, root was pointing to 3. So now root will point to 3. So friends, now in this step, as we have processed the left subtree completely, then now we'll process the node itself. So we are simply printing the data on the console. And then as we have to process its right subtree now, so we are calling inOrder method, and we are passing roots right, which is the null value. And before calling this new method, we are updating the line number. So when the point of execution reaches the inOrder method, root is null. So there will be one more method on the stack with a root as null. So now this root will point to null, and we'll start executing this method. So in the first step, we'll check whether root is equal to null or not. So currently root is equal to null, therefore we'll simply return from this method. And when we return, we know that this method will be removed completely from the call stack, and the point of execution reaches here. So we know that we'll execute this method from the line number 7, and we also know that at that moment root was pointing to 3. So now root will point to node 3, and then we'll start executing from the line 7. So when we reach to the line 8, we know that we have completely executed this inOrder method. So this will be removed from the call stack. So friends, now the execution point reaches to this inOrder method, and we'll start executing from the line 7. And we also know that when we are executing this method, root was pointing to 9. Therefore we'll simply traverse root to 9. And then we simply process all the steps for this inOrder method. So now this will be removed from the stack. So friend, as we know, there are no methods left on this call stack. Therefore we have successfully executed the in-order binary tree traversal, and the output you can see it's 4293. So friends, this was the demonstration of the algorithm. Now let's go to Eclipse and see the working code. So let's say I give the method name as public void in order, and as we discussed in the slide, this in order method takes in a root. Now in the first step we check if root is equal to null, then we'll simply return from this method, because this is the base condition. As we are calling this in order method recursively, we have to provide a base case so that we can get exit from this recursion. And as we discussed in our slide, that before visiting any node, we'll first visit its left subtree. So we'll call in order method and we'll pass root left to it. And after we process its left subtree, we will visit the node. So we simply print root's data on the console, and in the last step we'll again call in order method and we will process root's right subtree by calling root's right in the in order method. So friends, this is the algorithm for the in order binary tree traversal. Now let's test this working. Now in my previous tutorial, I had created one binary tree, and this is the same tree which we discussed in the slide. Use this create binary tree method. So here in the main method, we'll call create binary tree, and then we'll call the in order method, and here we'll pass the root. Now if I run the code, so here you can see it printed 4293, which is the same output which we saw in the slide. So friends, in my previous tutorial, we discussed about the recursive in order tree traversal. So steps involved in order tree traversal are as follows: that before visiting any particular node, we first visit its left subtree, then we actually visit the node, and then we visit its right subtree. And this steps is applied over each and every node. So friends, if we apply in order tree traversal over this tree, then what we need to do is, before visiting the node 1, we have to actually traverse its left subtree, then we have to visit the node, and after visiting the node we have to traverse its right subtree. So when we start with the node 1, we have to go to its left subtree first, because as we go to its left subtree, there is no way we can reach to the node 1 again. Therefore we need an additional data structure which can hold this node, so that once we complete the visiting of left subtree, we can pull the element out of that additional data structure and we can visit it, and after visiting it we can go to its right subtree. So the additional data structure that we use here is stack. So here you can see we are using stack, which is a LIFO data structure, which means the element inserted last into the stack would be the first one to be removed. In order to know more about the stack, you can watch my previous tutorials. Before visiting this node, we actually put it on the stack and then we go to its left subtree. And this we do for each and every node. And once we actually visit the left subtree of any node, then we pop the element out of the stack, we visit that node, and then we go to its right subtree. So let's see the demonstration of this algorithm step by step. So let's suppose we are given with a binary tree having 6 nodes and where root is pointing to the node 1. So let's apply this algorithm over this binary tree and let's see how we can traverse each and every node of a binary tree using the in-order tree traversal. So basically in the first step we check whether root is equal to null or not. So if root is equal to null, we simply return, because there are no nodes in the tree to be traversed. So currently you see root is pointing to node 1, therefore it's not null. So the condition in if block comes out to be false. So after the if block, what we actually do is we actually create a stack. Now this stack will hold the tree nodes for us. So it would look something like this. Moving ahead. So in the next step what we do is we create a temporary tree node and we assign the value of root to it. So now the temp will point to root. So it would look something like this. That is, temporary node is pointing to root. Moving ahead. So friends, in order to traverse this binary tree using in-order tree traversal, we actually use a while loop, and inside this while loop we are actually placing two conditions. So we are iterating this while loop till stack is empty and temp becomes null. So currently you can see stack is empty. So the condition comes out to be false. But you can also see the temp is actually pointing to a node, therefore it's not null. So the second condition comes out to be true. And as there is a OR operator between these two conditions, therefore the overall condition comes out to be true. So the while loop executes. So in the while loop we actually encounter an if else block. So in the if block we check whether temp is equal to null or not. So currently you can see temp is pointing to the node 1, therefore it's not null. So the condition in if block comes out to be true. So in the if block the first step we do is we actually push the temporary node on the stack. Which makes sense because before visiting this node we have to first visit its left subtree. So therefore we are actually pushing this temporary node on the stack so that once we are done with the left subtree, then we can pop this element out and then we can visit this node, and after visiting this node we can go to its right subtree. So when we push the temporary node on the stack, it looks something like this, that now node 1 is on the stack. Moving ahead, and in the next step we simply traverse the temp to its left because we have to first visit the left subtree. Therefore we need to traverse temp to its left. So we are assigning the value of temp dot left to temp. So here temp left is the node 2. Therefore now temp will point to the node 2. So it would look something like this. The temp is now pointing to the node 2. Moving ahead. In the while loop we'll again check whether stack is empty or not, and then we'll check whether temp is pointing to null or not. So currently you can see stack is not empty and temp is pointing to the node 2, therefore it's not null. So the condition in while block comes out to be true. And then in the if block we will check whether temp is equal to null or not. So here you can see temp is pointing to the node 2, therefore it's not null. So the condition in if block comes out to be true. And then we'll simply push that node 2 on the stack, because before visiting the node 2 we have to first visit its left subtree completely. Therefore we'll push the node 2 on the stack. So it would look something like this, that now node 2 is on the stack, and then we'll simply traverse temp node to its left, which is the node 4. So it would look something like this. Now temp is pointing to the node 4. And then again in the while block we'll check whether stack is empty or not and temp is equal to null or not. So currently stack is not empty and temp is pointing to the node 4. So therefore the condition in while block comes out to be true. And then in if block we'll check whether temp is equal to null or not. So currently temp is pointing to node 4, therefore it's not equal to null. So the condition in if block comes out to be true. So then in the first step what we do is we simply push the temp on the stack, because before visiting the node 4 we have to first traverse its left subtree completely. Therefore we are pushing the node 4 on the stack. So it would look something like this. Now node 4 is on the stack. Moving ahead, and the next step will simply traverse temp by assigning temp dot left value to temp. which makes sense because before visiting this node we have to first visit the left subtree. Therefore now temp has to move to its left subtree. So now temp will point to a node which is left to node 4, and here you can see it is pointing to null. So therefore now temp will point to null. Moving ahead, we'll again check whether stack is empty or not and temp is equal to null or not. So currently you can see temp is equal to null but stack is not empty. Therefore the condition in while block comes out to be true. And then in the if block we'll check whether temp is equal to null or not. So here you can see temp is equal to null. Therefore the condition in if block comes out to be false. So the else block will be executed. And here we can see that node 4 left is pointing to null. Therefore there is no node to be visited. So therefore we have visited its left subtree completely. So now is the turn that we can visit the node 4. So in order to do that, we'll simply pop the first element from the stack and we'll assign the temp to that node. So here you can see as stack is a LIFO data structure. So the last element inserted is the first one to be removed. So when we do a pop, the node 4 will be popped out and value of node 4 will be assigned to temp. So therefore, once the node 4 is popped out, temp will now point to the node 4. So it would look something like this. That now node 4 is popped out and whatever the value it holds, it will be assigned to temp. So now temp will point to the node 4. So it would look something like this. Moving ahead. So here for the node 4 we have visited its left subtree completely. So now is the time to visit the node 4. So on the console we are simply printing the data associated with the temporary node. So here node 4 becomes the first node to be traversed. So on the output 4 will be printed. Moving ahead. And as we have visited a node 4, now we'll simply traverse to its right subtree. So we are simply assigning value of temp.right to temp. So here temp.right is pointing to null. So therefore now temp will point to null. Moving ahead. So in the while block we'll check whether stack is empty or not. So currently stack is not empty. And temp is equal to null or not. So currently temp is equal to null but stack is not empty. Therefore the condition in while block comes out to be true. And we'll check whether temp is equal to null or not. So currently temp is equal to null. Therefore condition in if block comes out to be false. And the else block will be executed. So here you can see for the node 4 as its left is pointing to null and its right is pointing to null. It means there are no nodes on the left and the right side for the node 4 to be traversed. Therefore for the node 2 we have completely visited its left subtree because we have printed the output 4, which means we have traversed this node. So here what we are doing is we are again popping the element from the stack and we are assigning it to temp. So when we pop an element from the stack, we know that it's node 2. So it would look something like this. That node 2 is popped out and its value will be assigned to temp. So it means now temp will point to node 2. And which makes sense because we have completely traversed the left subtree for the node 2. So now it's the time to traverse the node 2. So in the next step, we'll simply print the data associated with the temporary node, which is 2. So on the console, we simply print 2. And then we'll simply traverse temp to its right. So here as we have visited the left subtree for the node 2 and we also visited the node 2, now is the time we go to its right subtree. Therefore we are simply assigning temp.right value to temp. So it would look something like this. So now temp is pointing to the node 5 because it is on the right of the node 2. Moving ahead. Now in the while loop we'll check whether stack is empty or not. So currently stack is not empty. And temp is also pointing to node 5. Therefore the condition in while block comes out to be true. And then in if block we'll check whether temp is equal to null or not. So currently temp is not equal to null because it is pointing to the node 5. Therefore the condition in if block comes out to be true. So what we do is we simply push the node 5 on the stack because we cannot visit this node till we visit its left subtree completely. Therefore we need a way to store this element on the stack. So we are simply pushing the temporary node on the stack. So now node 5 is on the stack, and then we simply go to its left because we need to traverse its left first. So now temp is pointing to null. In the while block we will check whether stack is empty or not. So stack is not empty, but temp is pointing to null. So the overall condition comes out to be true. So the while block executes. In the if block we'll check whether temp is equal to null or not. So temp is equal to null. Therefore the condition in if block comes out to be false, and the else block will be executed. So as node 5 has no left subtree, therefore it simply means that we have visited its left part. Now we'll actually visit the node. So we simply pop the element from the stack. So when we pop the element from the stack, we know that 5 was inserted last, therefore it would be first one to be removed. And when we remove the node 5, we assign its value to temp. So now temp will point to the node 5. So it would look something like this. So now temp is pointing to the node 5. And then we'll simply visit the node 5. So on the console we print the data associated with the temporary node, which is 5. Moving ahead. And once we have visited this node, now it's the time to go to its right subtree. So now temp will point to null. Moving ahead. In the while block we'll check whether stack is empty or not. So currently stack is not empty, but temp is pointing to null. So the overall condition comes out to be true because stack is not empty. So the while block executes. In the if block we'll check whether temp is equal to null or not. So temp is equal to null. Therefore the condition in if block comes out to be false, and the else block will be executed. So here you can see we have completely visited the node 5, and this node 5 is actually right to the node 2. Therefore we have completely visited the left subtree for the node 1. So when we pop an element from the stack, 1 gets popped out, and now temp will actually point to the node 1. So node 1 is popped out and its value will be assigned to temp. So now temp will point to node 1. Moving ahead. So friends, here you can see for the node 1 we have completely visited its left subtree by printing 4, 2 and 5. So now we can actually visit this node. So therefore we simply print the data associated with this temporary node, which is 1. So 1 gets printed on the console. Therefore we have visited this node. And in the next step, as we have visited this node, now we'll simply go to its right subtree. Therefore we simply assign temp right to temp. So here you can see temp right is pointing to the node 3. Therefore now temp will point to the node 3. Again in the while block we'll check whether stack is empty or not. So here you can see stack is empty. So the first condition comes out to be false, but here you can see temp is pointing to the node 3, therefore it's not equal to null. So the second condition comes out to be true. So here the overall condition comes out to be true and the while block executes. So here we will check whether temp is equal to null or not. So currently temp is pointing to the node 3, therefore it's not equal to null. So the condition in if block comes out to be true. And here before visiting the node 3, we have to first visit its left subtree completely. Therefore we need a way to store this element on the stack. So we simply push the temporary node on the stack. So it would look something like this. Now 3 is on the stack. And then we'll simply go to its left subtree, because this left subtree we need to visit first before actually visiting the node 3. So we are simply assigning temp.left value to temp. So here you can see temp left is pointing to the node 6. So therefore now temp will point to the node 6. In the while block we'll again check whether stack is empty or not. So currently stack is not empty. So the first condition comes out to be true and temp is actually pointing to the node 6. Therefore the second condition also comes out to be true. So the overall condition comes out to be true and while block executes. So in the first step we'll check whether temp is equal to null or not. So currently temp is pointing to node 6, therefore it's not equal to null. So the condition in if block comes out to be true. And then we'll simply push the node 6 on the stack, because we can't visit this node till we process its left subtree completely. Therefore we are storing the node 6 on the stack. So after pushing the node 6 on the stack, we simply go to its left subtree. So now temp will point to the left of the node 6, which is null. Moving ahead, now currently stack is not empty, but temp is pointing to null. Therefore the overall condition comes out to be true. We check whether temp is equal to null or not. So temp is equal to null, therefore condition in if block comes out to be false and the else block will be executed. So here as node 6 has no left subtree, therefore we are done with the processing of the left subtree for the node 6. So now is the time that we can visit the node 6. So what we do is we simply pop the element from the stack, because we know that we have actually stored this element on the stack. So we pop this element from the stack and we'll assign it to temp. So it would look something like this. So now temp is pointing to the node 6. Moving ahead. And then we are simply printing the data associated with node 6. So 6 gets printed on the console. And as we have visited this node, now is the time to go to its right subtree. So therefore now temp will point to null. So in the while block we'll check whether stack is empty or not. So currently stack is not empty. So this condition comes out to be true. But temp is pointing to null. So the overall condition comes out to be true. So the while block executes. We check whether temp is equal to null or not. So here temp is equal to null. Therefore the condition in if block comes out to be false. So the else block will be executed. So friends, here you can see for the node 6 we have actually visited its left subtree, we have visited the node, and we have visited its right subtree. So therefore we have completely visited his node 6, and here you can see node 6 is to the left of node 3. So now you actually traverse the left subtree for the node 3. So therefore now we can visit the node 3. So in order to reach to node 3, we know that we have already stored this node on the stack. So we simply pop this element from the stack and we'll assign it to temporary node. So it would look something like this. That node 3 gets popped out and its value is assigned to temp. So therefore now temp will point to node 3. And then we'll simply print the value associated with this temporary node, which is actually 3. So 3 gets printed on the console. And as we have visited the node 3 completely, now we need to visit its right subtree. Therefore we are simply assigning temp right to temp. So now temp will actually point to null. So now again we'll check the condition in while loop. So first we check whether stack is empty or not. So currently stack is empty. So the first condition comes out to be false. And then we'll check whether temp is equal to null or not. So here you can see temp is equal to null. Therefore the second condition comes out to be false. So overall both the conditions are coming out to be false. So the while loop terminates. And here you can see we have actually visited all the nodes of this binary tree, and we have printed the data associated with those nodes, which is 4, 2, 5, 1, 6, 3. So friends, this was the demonstration of the algorithm. Now let's go to Eclipse and see the working code. So in my last tutorial we actually discussed the recursive version of the in-order tree traversal. But in this tutorial we will discuss the iterative way for the in-order tree traversal. So here I will just comment this code, and below I will create the method as in order. Now this in order method will take in a root. So let's code the algorithm which we saw in the slide. So in the first step we'll check that whether root is equal to null or not. So if root is equal to null, we'll simply return from this method, because there are no nodes in the binary tree to be traversed. And the first step will create a stack which will hold the tree nodes for us. And as we discussed in the slide, we'll create a temporary node and we'll start it from the root. So tree node temp, and we'll simply assign the value of root to it. And now we'll simply provide a while loop. And we also saw that we have placed two conditions on that whether stack is empty or not. So the first condition is we are checking whether stack is empty or not, and then we are providing an OR. And the second condition we provide is temp should not be equal to null. So in the while loop we'll simply provide an if else block. So in the if block we'll first provide a condition that temp should not be equal to null, and if temp is not equal to null, then we simply push the temp on the stack, and then we traverse temp to its left. And if temp is equal to null, then we simply pop an element from the stack, and we will assign its value to the temporary node. Once we pop the element from the stack, we'll simply print it on the console. So temp dot data, and as we have printed the data on the console, then we'll simply traverse temp to its right. So friend, this is the code for iterative in-order tree traversal. Now let's test its working in the main method. So here first we have initialized the binary tree, and then we have created a binary tree with few nodes. So here in create binary tree we have actually created few nodes, which we also discussed in our previous tutorials. You can watch my previous tutorial in order to understand how this binary tree is created. And after creating the binary tree with few nodes, we'll simply call the in-order method and we'll pass the root to that method. So if I run this code now, so here you can see it prints 4293, because in the create binary tree the root is 9, and root left is second, which is 2, and root's right, which is 3. So So here 9 left is 2 and 9 right is 3, and here you can see second left is fourth. Now the fourth node is pointing to the second's left, so 9 is at the root, its left is 2 and its left is 4. So therefore, so on the console it printed 4, then it printed 2, and then 9 and then 3. Because as 9 is on the root, in order to process this node, we have to first visit its left subtree. So on its left is the node 2, and before processing the node 2, we have to go to its left subtree, so which is 4. So 4 gets printed first, then we print the node 2, and then we actually print the root node, and then we go to its right subtree, so we simply print 3. So friends, what is post order binary tree traversal? Basically there are 3 steps involved in doing the post order binary tree traversal, and all these 3 steps are applied over each and every node of a binary tree. So if we take an example of a binary tree shown in the slide, then basically we start with the root node and we apply these 3 steps over the root node. So what actually we do is, in order to visit this particular node, first we actually visit its left subtree completely, then we visit its right subtree completely, and then we actually visit the node. So here if we want to visit the node 1, then we have to first visit its left subtree completely, and then we have to visit its right subtree completely, and then we can visit the node. And these 3 steps are applied over each and every node. So suppose we are on node 2. So in order to visit this node, what we have to do, first we have to visit its left subtree completely, then we need to visit its right subtree completely, and then we can visit the node. So therefore here, before visiting the node 2, we have to first visit the node 4, then we have to visit the node 5, and then we can visit the node 2. So here basically these 3 steps are applied on each and every node of a binary tree in order to do post order binary tree traversal. So friends, in this tutorial we are discussing the recursive post order binary tree traversal. Below you can see the algorithm for the post order binary tree traversal. So we will demonstrate this algorithm using this binary tree here, and we will see how we can apply this algorithm on this binary tree, and whatever the output comes out, it will be displayed here. So friends, as this algorithm is recursive in nature, here you can see post order method is again internally calling the post order method. Therefore this is a recursive nature algorithm. So in order to understand the recursive nature of this post order method, we will maintain a call stack so that we come to know that which method is currently being executed and what is the route that is being processed. We will come to know about line number when we will actually discuss the post order method. So friends, let's see the demonstration of this algorithm step by step. So friends, here you can see the root is pointing to the node 9, and when we call this post order, we actually pass the root node. So to this post order, we are actually passing the root node as 9. So friends, when the point of execution reaches this post order method, we know that on the call stack there will be one method by the name post order, and we also know that we have passed the root as 9. So therefore on the call stack there will be one method by name post order which will start its execution. Moving ahead. So friends, the first step we actually check whether root is equal to null or not. So if root is equal to null, we simply return from that method, and here you can see that this condition will act as our base case, because as we are calling this post order method and internally again calls the post order method, we need to provide a base case to stop the execution of this post order method. Because if we don't provide the base case, post order method will again call post order method and it will go on calling each other infinitely. So this is the base case which is required in order to break the recursion, and we will see its significance later in the demonstration. So currently as you can see, root is pointing to 9, therefore it's not equal to null. So therefore the condition in if block comes out to be false. And at the line number 5, we see it calls post order method again, and this time we are passing roots left, which is the node 2. So friends, as we discussed in our previous slide, that in order to visit a particular node, we have to first visit its left subtree completely, then we have to visit this right subtree completely, and then we can visit the node. So therefore, before visiting the node 9, we have to first visit this left subtree completely. So we are again calling the post order method, and we are passing root.left to it, which is nothing but the node 2. So here you can see when we had called this post order method, there was one method on the call stack, and inside this we are calling this post order method again. So when we call this post order method, we are leaving this post order method. So in order to keep the track of this post order method, we will update the line number here. So it would look something like this, that from line number 5 we are leaving this post order method, and we are again calling the post order method with a root as 2. So once this line gets executed, we know that post order method will be called again, and this time this post order method will be called with the root as 2. So therefore the line of execution reaches to the post order method again, and we know that root will now point to the node 2. So now this method starts execution with a root as 2. Therefore we know that there will be one more method on the call stack. So here now this post order method will start its execution with a root as 2. Moving ahead, we will check whether root is equal to null or not. So here root is pointing to the node 2, therefore it's not null. So the condition in if block comes out to be false. And at the line number 5, we are again calling the post order method, and this time we are passing root.left. So here root left is nothing but the node 4. So why we are doing this step is because in order to process this node 2, we know that we have to first visit its left subtree completely, then we have to visit its right subtree completely, and then only we can visit this node. And we also discussed in our previous slide that all the 3 steps are applied to each and every node of the binary tree. So therefore before traversing the node 2, we have to first visit its left subtree completely. So therefore we are calling this post order method again with a root as 4, and we also know that we are leaving this post order method, so we will update the line number here, which is nothing but 5. So now point of execution reaches to this post order method with the root as 4, and we also know that now root will point to the node 4, and as this method will start its execution, there will be one more method on the call stack with the root as 4. So here now this post order method will start its execution with the root as 4. So in the first step we will check whether root is equal to null or not. So currently root is pointing to the node 4, therefore it's not null. So the condition in if block comes out to be false. And then on the line number 5, we are again calling post order method with the value as root.left. So friends, in order to process the node 4, we have to first visit its left subtree completely, then we have to visit its right subtree completely, and then only we can visit the node 4. Therefore we are again calling the post order method, and this time we are passing the value as root.left. So here root is pointing to node 4 and its left is pointing to null. Therefore now we are calling this post order method with a null value, and we also know that we are leaving this method from the line number 5, therefore we will update the line number here as 5. So the point of execution will reach to this post order method with a root as null. So therefore now root will point to null, and we also know that there will be one more method on the call stack by the name post order, and whose root will be null. So now this post order method will start its execution with a root as null. So here first we will check whether root is equal to null or not. So currently you can see root is pointing to null, therefore the condition in if block comes out to be true. So therefore we have reached our base case. So we'll simply return from this method. So friends, as we return from this method, we know that this post order method is executed completely, therefore this method will be removed from the call stack. So friends, when this method is removed from the call stack, the call goes to its previous method, which actually called this method with a root as null. And we also know that we had left this post order method from the line number 5. So the point of execution reaches to this node and we'll start our execution from the line number 5. Because at this line number we have actually left this method, so therefore we'll start our execution from this line. And we also know that when we had left this method, at that moment root was pointing to node 4. So therefore now root will point to node 4. Moving ahead. So friends, at the line number 6 we are again calling the post order method, but this time we are passing it a value as root.write, which actually makes sense because in order to traverse this node 4, we have to first visit its left subtree completely, then we have to visit its right subtree completely, and then we can visit the node. So therefore on the line number 5, we have completely visited the left subtree for the node 4. So now is the time to visit its right subtree. So therefore we are again calling the post order method and we are passing the value as root.write. So here root is pointing to node 4 and its right is pointing to null. Therefore we know that now we'll call this post order method with a null value. And we also know that as we are leaving this post order method from the line number 6, we need to update the line number here. So the line number becomes 6. So friends, point of execution reaches to this post order method and this time the root will be null. And we also know that once this method starts its execution, there will be one more method on the call stack with the root as null. So it would look something like this. So we know that root is null. So therefore now root will point to the null. Moving ahead. We will check in the if log whether root is equal to null or not. So currently you can see root is equal to null. So therefore we'll simply return from this method. And as we return from this method, we know that this method is executed completely. So this would be removed from the call stack. And the point of execution reaches to the post order which actually called this method. And we also know that we had left this post order method from the line number 6. Therefore the execution will start from the line number 6. And we also know that when we had left this method, root was pointing to the node 4. So therefore now root will point to node 4. Moving ahead. So friends, on line number 7, we will simply print the data associated with this root. So friends, in order to process the node 4, what we have actually done is, we have first visited its left subtree completely. Then we visited its right subtree completely. So after doing this stuff, we are actually visiting the node 4. So we are simply printing its data on the console, which is 4. Moving ahead. So friends, at the line number 8, this post order method on the call stack will complete its execution. So this would be removed from the call stack completely and the point of execution will reach here. And we also know that we had left this post order method from the line number 5. So the point of execution reaches to the line number 5. And we also know that at that time root was pointing to node 2. So here now root will point to node 2. And we'll start our execution with this post order method. So friends, in the line number 6, we are again calling the post order method. And this time we are passing root.write to it. So here you can see root is pointing to node 2. So we'll pass root.write, which is null, to this post order method. So friends, here you can see we are calling this post order method again with the root as null, because root.write is nothing but null value. And we also know that we are leaving this method, so we'll update the line number here. And we know that line number is 6. So now line number changes to 6. So root is pointing to the node 2. Therefore now it will point to its right, which is null. Now this method will start its execution. So therefore there will be one more entry on the call stack with a root as null. Moving ahead. we'll check whether root is equal to null or not. So currently root is equal to null. So therefore we'll simply return from this method. So when we return from this method, we know that this post order method is executed completely. So therefore it will be removed from the call stack. And once it's removed from the call stack, the point of execution reaches to this post order method. And we also know that we have left this method at the line number 6. So we'll start its execution from the line number 6. And we also know that when we had left this method, root was pointing to node 2. So here root is pointing to null. So now it will point to node 2. Moving ahead. And at the step 7, we'll simply print the data associated with the root, which is nothing but 2. So friends, here you can see, before processing of the node 2, we first completely visited its left subtree and we printed node 4, and then we visited its complete right subtree, which was actually null, and then we actually visited the node 2. So it printed something like this, 4 and then 2. Moving ahead. So at line number 8, we know that this post order method is being executed completely. So therefore this would be removed from the call stack. And the point of execution reaches to this post order method. And we also know that when we had left this post order method from the call stack, the line number was actually 5. So we'll start our execution from the line number 5. And we also know that root at that time pointed to the node 9. So therefore now root will point to node 9. And our execution starts from line number 5. So friends, here you can see that we are on node 9. And in order to visit this node, we have to first visit its left subtree completely, which you have actually done. And then we have to visit its right subtree completely. So now we'll start to move to its right, and then we can process this node 9. So we are again calling the post order method, and this time we are passing the value as root.right, because we have to now visit its right subtree completely. So therefore you can see root's right is nothing but node 3. So we will be again calling this post order method with a root as 3. And we also know that we are leaving this method post order from the line number 6. So therefore we'll update the line number here. So now point of execution again starts post order method, and this time with the root as 3. So now root is pointing to the node 3, and we also know that there will be one more method on the call stack with the root as 3. So friends, now let's start the execution of this post order method with the root as 3. In the first step, we will check whether root is equal to null or not. So currently root is pointing to node 3, therefore it's not null. And at the line number 5, we will again call post order method, and this time we are passing roots left, which is nothing but the null value. So here, before processing of node 3, we know that we have to first process its left subtree, and then we have to process its right subtree. So in order to process its left subtree, we are calling this post order method again with roots left, which is nothing but the null value. So friends, we are leaving this post order method at line number 5. So we will update the line number here. And then point of execution will call this post order method again with root as null. So now root will point to null. And we also know that there will be one more method on the call stack with a root as null. So now let's execute this post order method with the root as null. So here we check whether root is equal to null or not. So currently root is equal to null. Therefore we'll simply return from this method. So once we return from this method, we know that this method is executed completely. So it will be removed from the call stack, and point of execution will reach to this post order method. And we know that we had left this post order method from the line number 5. So therefore we'll again start our execution from the line number 5 with the root as 3. So currently root is pointing to null, so now it will point to 3. So we are starting from line number 5 and now root will point to node 3. Moving ahead. So at the line number 6 we will call post order method again and we'll pass the value as root.write, because in order to traverse this node we have to traverse this left subtree first, which we have already done. So now is the time to traverse this right subtree, and after traversing right subtree we can actually visit this node 3. So in order to visit its right subtree we are calling this post order method again and we are passing the null value to it. And we also know that we are leaving this method at line number 6, so we'll update the line number here. So now point of execution will start the execution of this new post order method with the root as null. So root is pointing to node 3, now it will point to null. And we also know that there will be one more method on the call stack with the root as null. So let's start the execution of this post order method with the root as null. So we'll check whether root is equal to null or not. So currently root is equal to null. Therefore we have actually visited the right subtree for the node 3. So we'll simply return from this method. And as we return from this method, this post order method will be removed from the call stack and point of execution will reach to this post order method. And we know that we have left this post order method from the line number 6 with the root as 3. So we'll start the execution from the line number 6, and we know that at that time root was pointing to 3. So now root will point to node 3. So friends, we have visited the left subtree for the node 3 and we also visited the right subtree for the node 3. So now we can actually visit the node 3. So on the line number 7, we will simply print the data associated with this root, which is nothing but 3. Moving ahead. And once we reach the line number 8, we know that we have successfully executed this post order method. So this method will be removed from the call stack and the point of execution will reach to this post order method. And we also know that we had left this post order method from the line number 6 and at that time the root was actually 9. So we are starting from the line number 6 and we know that we had left this method when the root was pointing to 9. So therefore now root will point to 9. Moving ahead. So friends, here you can see for the node 9 we have completely visited its left subtree and we have printed 4 and 2. Then we actually visited the right subtree completely and we printed 3. So now is the time to visit the node 9. So we are simply printing the data on the console for the root which is pointing to node 9. So now 9 will be printed on the console. And from the line number 8 we know that we have completely executed this post order method. So this would be removed from the call stack. And once this is removed from the call stack, we know that there are no more methods left to be traversed. So here we have actually successfully executed this recursive post order traversal to this binary tree and we have printed its each and every node on the console as 4, 2, 3, 9. So friends, this was the demonstration of the algorithm. Now let's go to Eclipse and see the working code. So in this tutorial we will actually code recursive post order traversal of a binary tree. So here I will create one method as public void post order. So this is the same method which we discussed in the slide. So this method takes in a root which is of type tree node. So first we'll provide the base case, which is we will check whether root is equal to null or not. So if root is equal to null, then we'll simply return from this method. So this is nothing but the base case because we are calling this post order method recursively. So friends, as we discussed in our slide, that in post-order tree traversal, before visiting any node, we'll first visit his left subtree, and then we'll visit his right subtree, and then we can visit the actual node. So first we'll visit the left subtree by calling root.left, and then we'll visit its right subtree by calling root.right. And after visiting the left subtree and the right subtree, we'll actually visit the node. So we'll simply print root.data on the console. So friend, this is the code for recursive post order binary tree traversal. So now let's test its working on the main method. So here in the main method, we'll first initialize this binary tree class, and then we'll create the binary tree. So in create binary tree method, we are actually creating the binary tree with few nodes, and these are the same nodes which you discussed in the slide. And we also discussed this method in my previous tutorials. So you can watch my previous tutorials in order to understand how we have created this binary tree with the few nodes. So after creating this binary tree, we'll actually call the post order method, and we'll also pass the root into it. So if I run the code now, so you can see it printed 4239, which is the same output which we discussed in the slide. So here you can see, let's say we are given with this binary tree, and we want to traverse this binary tree using the iterative post order traversal. So in our previous video, when we discussed about the recursive approach to traverse the binary tree, we discussed that in order to traverse a binary tree using post order, what we do is, before visiting the root, we visit all its element on the left subtree, then we visit all its element on the right subtree, and then we actually visit the root. And usually these three steps we perform on each and every node of a binary tree when we do the traversal in a recursive way. So in case you want to learn more about that, you can watch my previous video. So the only thing we need to remember here is, when we do post order traversal, on every node we need to first traverse all its elements on the left side, then we need to visit all its elements on the right side, and then we can actually visit the node. So for example, if we are on node 2, then we can't directly visit the node 2. We need to visit first the node 4, then we need to visit node 5, and then only we can visit the node when we are performing the post order traversal. So in this video we will discuss the iterative approach where we are not performing any recursion. So when we perform post order traversal using the iterative way, we usually take the help of a stack. So stack is nothing but a LIFO data structure, which means last in first out, where the last element inserted will be the first one to be removed. So we will use the stack data structure to traverse this binary tree using the post order traversal. So let's see the demonstration of this algorithm step by step. So at the first step, what we do is, we create a tree node current which simply points to the root. And in the middle of this algorithm, we are also creating one temporary tree node. We will see their advantages later in the algorithm. So in the first step, we are simply creating the current and pointing it to root. Then we are actually creating the stack data structure. So this is our stack data structure, and we are using the stack class present in Java. So as we want to perform this post order traversal, we need to visit each and every node of this binary tree. And as we are following an iterative approach, we are providing a while loop where we are providing the two conditions. First is the current is not equal to null, or stack is not empty. So here you can see current is pointing to a node having value as 1. Therefore this condition comes out to be true because current is not equal to null. So the overall condition of this while loop comes out to be true because any of this condition if comes out to be true, this while loop will execute. So here you can see in the first step what we are checking is that if current is not equal to null, then we simply go inside this if block, or else we perform this logic. So why we are providing this condition here is, let's say current is pointing to a node having data as 1, and let's suppose we want to visit this node. So if the current is not equal to null, then we can't directly visit this node. We need to first visit all the elements of its left subtree, and then we need to visit all the nodes of its right subtree, and then only we can visit this node. So current will be null at this location, and when current will be null, then we can simply decide that now can we visit the node or not. So here as current is not equal to null, so there can be a possibility that this node has a left subtree. So what we do is, we simply push node 1 into the stack, and then we simply traverse to its left by assigning current's left to current. So current is pointing to node 1, its left is pointing to node 2. So now current will point to node 2. We again check where current is equal to null or not. So current is not equal to null. So the first condition comes out to be true, and we don't evaluate the second condition because of this OR operator. So this while loop will execute. We check whether current is equal to null or not. So current is not equal to null. So this condition also comes out to be true because there can be a possibility that node 2 has a left subtree. So what we do is, we simply push the current on the stack. So 2 will be on the stack, and then we simply visit current to its left. So current will now point to 2's left, which is 4. And similarly current is not equal to null, so this condition comes out to be true. Here current is not equal to null because it is pointing to node 4. So we simply push current onto the stack because there can be a possibility that there is a left subtree or a right subtree. So 4 is on the stack, and we go to its left by assigning current's left to current. So current will point to its left, which is null value. So friends, here you can see now current is actually pointing to null. Now if the current is pointing to null, so this null can be on the left side of this node or on the right side of its node. So if the current is on the left side of the node, then we know that we need to visit the right side also before visiting this node. But if the current is on the right side of the node, then we know that we have already visited left, we have already visited right, now we can visit this node. So in the post order we discussed that in order to visit any node, we need to visit all its left children, then we need to visit all its right children. So if current is pointing to a null, then there can be two possibilities, that this null value can be on the left side and this null can be on the right side. So if the null is on the left side, we need to visit the right subtree for this node. And if the current is on the right side, then we know that we have already visited left and we have already visited right. Then we can simply visit the node. So here current is equal to null. So this condition comes out to be false. But our second condition, the stack is not empty. So this condition comes out to be true and overall condition comes out to be true. So while loop will execute. This if check will fail because current is actually pointing to null. So now we'll go to the else part. So in the first step what we do is, we create a temporary variable and we assign a value stack.peak.write. So here you can see in the stack whichever is the last element inserted is the peak of the stack. So when we do stack.peak, we are simply pointing to this node 4, and if we do .write, then we are actually pointing to nodes write. So here this is 4 and write will be null. So we will see why we are creating this temporary variable. So for timing, you can see that temp is pointing to null. Now here we are given two conditions, that whether temp is equal to null or temp is not equal to null. So why we have provided this condition is because, let's say if current is pointing to null, then we need to somehow check that whether this null value is on the left side of node 4 or on the right side of the node 4. So in order to verify that thing, we created this temporary node. So as current is pointing to null, so this can be any left or right child of a node. And we also know that this node will be already present on the stack. And if we want to know that whether we are on the left side or on the right side, what we do is we simply go to this node and go to its right. So here temporary variable is doing that for us. So here why we are providing this check here is if temp is equal to null. So this will signify that whatever the value was on the stack, its right is actually pointing to null, and there are no nodes left to be traversed on the right side of this node. So what we can simply do here is pull this element out, because we are now sure that as current is pointing to null and temporary is pointing to null, which means that we have traversed the left subtree and the right subtree for this node. So now we can simply pull this node out and we can simply visit it. So we'll pull this element out, and now temp will point to 4. And in the next step, we'll simply visit the temp. So we are simply printing the data of the temp, which is 4 here. So friends, why we actually do all this stuff is when current actually reaches to any null value, then we need to be sure that whether it's on the left side or on the right side. So we simply create a temporary variable to simply peek the right side of a node present in the stack. And if the temp is equal to null, then it simply signifies that there are no nodes on the right side and we have already visited the left side. So now it's time to visit the actual node. So we have visited 4 here. Moving ahead. So friend, now here we provide a while loop. And why we have provided a while loop? Because the first thing we are checking is stack is not empty. So as we have recently pulled an element out of it, so there can be a chance that stack becomes empty. So stack should not be empty. And the second condition is very important, which is the core of this algorithm, is we are simply checking whether temp is stack.peaks right. So here you can see, so as we have recently visited this node here, so there can be a possibility, and we need to be sure that whether this node is on the left of 2 or on the right of the 2. Because if it is on the left of 2, then we can't directly visit 2, we need to go to its right and visit node 5. But if it is on the right side, then we can simply visit the node 2. So here stack peak is node 2, this, and its right, which is this value, is node 5. So we are simply checking whether this node which we visited just now, its value is equal to its parent's right or not. So if this value comes out to be true, then we know that parent right is actually the node which we just now visited. So we can simply visit the parent now. But here you can see temp is pointing to 4 and stack peak, which is the node 2, is pointing to right. Therefore they are not equal, which means that whatever the node we have visited just now, it's on the left side, not on the right side of node 2. So this while loop will terminate and our call will reach to this while loop again. So friends, here why we have provided this while loop, it will be clear when we reach here. So for timing, you can just think that we have provided a while loop here. So moving ahead, here you can see current is pointing to null, but stack is not empty. So the overall condition comes out to be true. current is equal to null. So we go in the else. Now in the first step what we do is we simply assign the stack peak's right value. So stack peak is node 2, this node, and its right is node 5. So temp will point to 5. So friends, why we are assigning this value now here is, as current is pointing to null and we have recently visited node 4, and we also verified here that node is at the left of 2. So there can be a possibility that node 2 might have a right subtree, and in post order traversal, after visiting the left part, we need to visit the right part, and then only we can visit the parent. So here we are simply assigning the value of stack.peak.right. So 2's right is 5, so temp will point to 5. And here we will check whether temp is equal to null or not. So here temp is not equal to null, which signifies that the right part, there is a node which also can have left and right children. So, and we can't directly visit this node because there might be a possibility that it contains left and right children. So here, if this condition comes out to be false, and we go in the else part, where we'll assign the current to the temp. So why we are assigning current to temp? Because this 5 can be treated like any other node which can have the left and right children. So as we started by pointing current to root, it is similar to that step that this node can have a left or a right children. So we need to perform all those steps again on this node. So here current is not equal to null. So this condition comes out to be true. And if the current is not equal to null, so this is the same case which we discussed here, that current is not equal to null. There can be a chance that this node have a left children. So what we do is, we first push the 5 on the stack, and then we go to its left by assigning current's left to current. So current will point to null. So as current is pointing to null, so this condition is false, but our second condition is true because stack is not empty. And here you can see current is equal to null. So this condition also comes out to be false. And we go into the else part. In the first step we are assigning stack peak's right value to temp. So stack peak is node 5, this node, and its right is this value. So we are assigning null to temp. And then we are simply providing this check because if temp is null, then we know that current is already pointing to null, which is the left part, and temp is also pointing to null, which is the right part. So which signifies that its parent has no left and right children. So we can simply visit the parent now. So in the first step what we do is we poll the topmost element, which is the node 5, and we'll assign it to temp. So first this will poll out and temp will point to 5. So we can safely visit this node because we have already visited its left and right children. So 5 will be visited here. And then we are providing this while loop, which we will discuss when we reach here. So just for timing, think that we are providing this while loop to check whether the node which we have visited is on the left or on the right side of its parent. So currently stack.peak is 2, which is parent to 5. And if we see here, dot right is this value only, and temp is also pointing to this node. So this condition temp equal stack.peak.right is actually true because we are on the right side of the parent and we have already visited this node. So now we can simply poll this element out and we can simply visit because we have already visited its left part and the right part. So this while loop condition will come out to be true. We are polling 2 out and temp will point to node 2, and then we are simply printing the data of this node by visiting it. So 2 will be printed. So as it is a while loop, we are again checking that whatever node we visited just now, is it on the left side or on the right side of its parent. So the first condition is stack should not be empty because we have recently pulled an element out. So there can be a possibility the stack is empty. So here stack is not empty. And the second check verifies that whatever the value we have here, which is the parent to this node. So here we are simply verifying that this temp is on its left or on its right side. So temp is actually on the left side. So this condition comes out to be false. So our execution point reaches to this while loop, where here you can see current is equal to null, but stack is not empty. So here current is equal to null. So this condition comes out to be false. In the else part, we will assign stack.peak.write value to temp. So stack.peak is 1 and its write is node 3. So temp will now point to node 3. Moving ahead, we check whether temp is equal to null or not. So temp is not equal to null. So this condition comes out to be false. So if this condition would have come out to be true and temp would have pointed to null, then we could have visited this node directly. But as temp is not equal to null, so there can be a possibility that this node can have left or right children. So we simply go to the else part and we assign the value of temp to current. So now current will point to this node because we have figured out that there can be a possibility that 3 can have left or right children's. So current will point to 3. So now this is the same situation which we saw in the start, that current is not equal to null. And if current is not equal to null, there can be a possibility that there could be a left children of it. So we are simply pushing the current onto the stack. So 3 will be on the stack. And then we go to its left by assigning current's left to current. So current will now point to null. So as current is equal to null, but stack is not empty, this overall condition comes out to be true. So we check whether current is equal to null or not. So current is equal to null. So in the else part, we will assign stack's peak write value to temp. So stack peak is node 3 and its write is 6. So now temp will point to 6. And here we check whether temp is equal to null or not. But here you can see temp is not equal to null. So there can be a possibility 6 can also have left or right children. So in the else part, we simply assign current to 6. Current is not equal to null. And in the if check also, current is not equal to null. And there can be a possibility that 6 can have left children. So we push 6 on the stack. And we go to its left by assigning current left to current. So current will point to null now, which is the left of 6. Current is equal to null, but stack is not empty. So this condition comes out to be true. And overall condition comes out to be true because of this OR operator. Here the if condition comes out to be false because current is pointing to null. And then we simply assign stack.peak.write to temp. So stack peak is node 6, this node, and its write is this node. So temp will now point to null. And here we are providing this check that if temp is equal to null, which means that current is pointing to null, and whatever its parent is, its write is also pointing to null. So we can safely visit this node, which is the parent. So how we can safely visit that node is, first we'll pull that element out of the stack. So 6 will be pulled out and temp will point to 6. We will visit this node. So 6 will be visited. Now friends, here we encountered a while loop and we discussed that why we are providing this while loop is because the first check is stack should not be empty. So stack has 2 nodes, therefore it's not empty. Now as we have recently visited this node, so after visiting this node, we need to be very much sure that whether this node was at left or was at right to its parent, which is 3. We can access 3 by stack's peak, which is by getting this value. And if we call dot right, then we'll reach here only. So if temp is equal to this value only, then we know that we are actually on the right side of temp's parent, which signifies that we have already visited the left part, we have completely visited the right part, and now we can simply visit the parent. So here we poll the parent out and temp will point to 3. We visit 3 and we again encounter the while loop. So friends, here you can see that this while loop is provided because if this is the condition here, then here you can see that stack is not empty. And as we have visited 3, so this 3 can also be the right child of its parent. So therefore we are providing this while loop. Let's say if this chain goes on like this and there are no left nodes, so this while loop will simply make us traverse back because all these nodes are on the right side of its parent, which we already visited. So that's why we are providing this while loop. So here again we are simply checking whether temp is pointing to its parents right or not. So here stack.peak will give us 1, its right will give us node 3, and temp is also pointing to node 3. So this while loop condition will come out to be true and we can simply poll 1 out because we have visited all the left subtree of the node 1 and we have recently visited all the nodes on the right subtree of 1. So we can simply poll the 1 out. Temp will point to 1 and we can simply visit node 1 now. So node 1 will be visited here. And finally, we again check whether stack is empty or not. So here you can see we have recently polled one element out. So stack is empty. So this condition comes out to be false and the while loop will terminate. And once the while loop will terminate, our call will reach here. So here you can see current is equal to null. This condition is false and our stack is also empty, which signifies that we have completely visited this binary tree using the post order traversal. So this whole condition will come out to be false. So friends, here you can see that using a stack, we visited all the nodes of this binary tree using the post order traversal. So this was the sequence. First 4 was visited, then 5 got visited because before visiting 2, we need to visit its left part, then we need to visit the right part, and then we can actually visit the node. So 2 was visited after that. Now we can't directly visit 1 because we need to traverse all the nodes of its right subtree. So we reached here. We saw that 3 didn't have any left part. So we can't visit 3 directly. We went to its right. We saw that 6 left and right both are null. So we simply visited 6 then. After we visited 6, which was on the right side, we safely visited 3. And 3 was also on the right side, so we safely visited 1. So this is the post order traversal of a binary tree. So in this video we'll see the post order traversal of a binary tree using the iterative approach. So here I will be creating one method as public void. I will give a name as post order. So here when we discussed post order traversal using the recursive approach, we saw that before visiting the node's data, we need to visit first its left subtree, then we need to visit its right subtree, and then only we can visit the node's data. So this was a recursive approach which got implied on each and every node of the binary tree. So when we perform the iterative approach, we usually use the while loop and we traverse each and every node of the binary tree, keeping the post order traversal in mind. And the data structure will help us doing this is the stack data structure, which is the LIFO data structure, which is also known as the last in first out. So the last element inserted inside that data structure will be the first one to be removed. So we discussed this algorithm step by step in our previous video using an animation. So now let's code the algorithm and test its working. So in post order method, the first thing we do is we create a tree node current which starts from the root of the binary tree whose traversal we need to do. In the second step, we create a stack which will hold our tree nodes. We give it a name as stack, and we are using java.utils stack class. We can also use our stack which we discussed in our previous videos, but here I will be using the java.utils stack. Now in order to perform the post order traversal, we need to provide a while loop, and inside that while loop we provide a condition as current should not be equal to null or stack should not be empty. So here you can see that current is pointing to root, and we need to go inside this while loop to traverse each and every node of the binary tree using post order. So the first condition we provide is current should not be equal to null, and when current is equal to null, then the logic we apply we'll see later in the algorithm, and the other thing is the stack should not be empty. So here you can see in this while loop we provide a condition as current not equals to null. So if current is not equal to null, then it signifies that we can't visit the current directly. We need to first go to its left subtree and visit that. Then we have to go to its right subtree and visit that, and then only we can visit that particular node. So if current is not equal to null, so there is a possibility that current might have a left subtree. So the first step we do is we simply offer, or you can say push, the current on the stack, and after pushing current on the stack we simply go to its left by assigning current's left value to current. And if current is equal to null, then we provide else part, where what we do is we create a temporary node and we assign the stack's peak values right to it. So friends, here if the current is pointing to null, then we need to follow these steps to identify that whether that current is actually the left child of the parent or at the right child of the parent, because if it is the left child of the parent, then we can't visit parent directly, we need to go to its right first. But if it's the right child of the parent, then we can simply visit the parent. So if the current is equal to null, in order to identify that, the first thing we do is we take its parent which is on the stack and we'll simply assign the right value to temp. So here, after getting this temp, there are basically two conditions. One is, what if the temp is also null? So this check basically signifies that if temp is pointing to null, and as we have moved to parent's right and temp is pointing to null, it means that there are no right children of the parent. So we can simply visit the parent, because when we do post order traversal, In order to visit the parent, we first visit its left subtree and then we visit its right subtree, and then only we can visit the parent. And as we are on the right part and that is coming as null, it means that we have visited the right part and now we can safely visit the parent. So here what we do is we simply pop the element from the stack and assign it to the temp. So once the temp is pointing to parent, what we do is we simply visit the parent by printing its data on the console. And after visiting the node, we again provide a while loop. And inside that while loop, we provide the condition as stack should not be empty, because we have recently popped an element from the stack, so stack can be empty. So here we are providing this one condition that stack should not be empty till this point. And so here, as we have visited this node, now this node can be a children of its parent and it can be on the left side or on the right side. So there are also now two conditions coming up here. If the temp is on the left side, then we know that we need to go to the parents right now because we have visited the temp here. But if the temp is on the right side, then we know that once we have visited the right side, we can simply visit the parent. So here we need to provide one more condition as if temp is equal to stack dot peak dot right. So this condition signifies that whatever the peak values are on the stack, it would be parent to temp. And if its right value is equal to temp, it means the temp is on the right side. So if it is on the right side, then we can simply again pull the element from the stack, assign it to temp, and we can simply visit that. And also friends, as here we are popping out an element and visiting it, we need to provide this in while loop because there can be a chance that whatever we are visiting, it's actually coming out to be the right of the parent. So once this condition comes out to be true and we pop the parent from the stack, there can also be a chance that whatever we visited here will also be on its right of its parent. So we need to provide this while loop because whenever we are visiting any element by printing it on the console here or here, we need to simply perform this check that what we visited was at the right of its parent or was it at the left of its parent. So if it is on the right of its parent, which is this condition, then we'll simply keep on popping the element out and simply printing its data. Because in the post order traversal, this is the main step, that once the right children of any node is visited, then only we can visit the parent. So here this condition is signifying that only. So this was the part in the if condition. And let's say if the temp is not equal to null, it means that when we peeked the parent element and we went to its right, that was not null. So before visiting right directly, there can be a possibility that right also has left or right children. So therefore, these two checks are important. If temp is null, then we are sure that right is already visited. We pop the element out, we print its data, and then we again check it for its parent. But if the temp is not equal to null, then we know that we need to visit the right part also. And once we go to its right part, the right part can also have its own left and right children's. So here, now our condition becomes something like this, what we did here. So here what we do is, we simply assign the value of temp, because it is not equal to null, to current. So friend, this was all about this algorithm. Now let's test its working in the main method. So friends, here you can see that in our previous videos we created one binary tree with these hard-coded values So where root was pointing to 1, 1 had two children's, left and right as second and third, this 2. Second had two children's left and right as fourth and fifth, this 2. And third node had left and right as sixth and seventh, so these 2 nodes. So here 1 is at the root, second and third are its left and right children, 4 and 5 are left and right children of 2, and 6 and 7 are left and right children of 3. So this was the hard-coded binary tree. So here after creating this binary tree, what we can do is, we can simply call the post order and we can run the program. So friends, here you can see it printed 4, 5, 2, 6, 7, 3, 1. Here in this binary tree, before visiting 1, which was the root, we need to visit 2 and 3. So 2 was at left. So when we reach to 2, we can't visit 2 directly because 2 also has left and right children, which is 4 and 5. So when we reach to 4, we found that 4 didn't have any left and right children. So the first thing we visited was 4 because this was the left of 2. And then we visited 5 because 5 was right of 2. And after visiting the left and right children, we visited 2 here. And once we visited 2, we know that we have visited all the left children of the actual root. So now it was time to go to its right binary tree. So when we went to 1's right, we found 3. So we can't visit 3 directly because 3 has a left and right children, which is 6 and 7. So when we went to 6, we found that 6 didn't have any left and right children. So we safely visited 6. And then we safely visited 7 because 7 was right to 3. So after visiting 6 and 7, which was the left and right children of 3, now we can safely visit 3. And once we visited 3, we were pretty much sure that we have visited all the nodes of the right subtree of the actual root, which was 1. So finally we visited 1. So friend, this was all about the post order traversal. So friends, what is the level order traversal? So here we use this traversal technique to visit the nodes of a binary tree level by level. So here you can see the root is at level 0, 2 and 3 are at level 1, 4, 5, 6 are at level 2. So in this traversal technique, we first visit the level 0, then we visit the level 1 and then we visit the level 2. So when we actually visit the node and print its data on the console, so it will be like first 1 will be printed, then 2, then 3, then 4, 5 and 6. So here when we do a level order traversal of a particular level, then we actually store the elements of its next level on an additional data structure, which is nothing but the queue. So here suppose we are visiting the node 1, then on the queue we put the node 2 and node 3, so that after visiting the node 1 we can pull the node 2 and node 3 and we can visit them. And while we are visiting the node 2, we put 4 and 5 on the queue, and when we are visiting the node 3, we put node 6 on the queue. So therefore it goes level by level, and the additional data structure which we use to store this element is a queue. So basically in this traversal we are using queue because it is a FIFO data structure, which is nothing but first in first out. So the element inserted first will be the first to be removed. We will see its significance when we demonstrate the algorithm. So let's start execution of this algorithm step by step. So let's suppose we are given this binary tree where root is pointing to the node 1. So when this algorithm starts, we first check whether root is equal to null or not. So if root is equal to null, then we simply return from the method because there are no nodes in the binary tree to be traversed. And here you can see as root is pointing to the node 1, therefore the condition in if block comes out to be false. And in next step what we do, we first initialize the queue data structure. So here you can see the queue data structure where nodes are entered from one end and they are removed from the other end. So this property makes queue a FIFO data structure, that is the element inserted first is the first one to be removed. And in order to know more about the queues, you can watch my previous tutorials on the queue data structure. And in this tutorial we will use the Java implementation of the queue, which is nothing but a linked list. So we will initialize the queue by creating the instance of the linked list. So after creating the queue, what we first do is we offer the root node to the queue. Here offer is nothing but the enqueue operation where we add the element to the queue. So in the first step what we do is we offer the root node to the queue. So it would look something like this. As root is pointing to node 1, therefore in the first step what we do is we basically add node 1 into the queue. So it would look something like this. That is the node 1 is in the queue. Moving ahead. So friends, in order to traverse this binary tree using the level order traversal, we basically use a while loop. And inside this while loop we place a condition as that we will iterate this while loop till queue is empty. So currently you can see queue is having one node, which is node 1, therefore it's not empty. So the condition in while block comes out to be true. So in the first step what we do is we actually pull the element from the queue and we assign it to the temporary node. So here you can see queue is having one tree node having data as 1. So when we perform a poll operation on the queue, node 1 will be removed and its value will be assigned to temp. So it would look something like this. So node 1 is removed from the queue and temp is now pointing to the node 1. So whatever the value we pulled from the queue, we simply assigned it to the temporary node. Moving ahead. So after pulling the node from the queue, we simply print its data on the console. So 1 got printed on the console. It means we have visited the node 1. And as we discussed earlier, that when we visit any particular level, we store the elements of its next level on the queue. So here we first check that whether temp.left is equal to null or not. So temp is pointing to node 1 and its left is pointing to node 2. Therefore the condition in if block comes out to be true because temp.left is not equal to null. So in the if block we simply offer temp.left element to the queue, which is nothing but the node 2. So it would look something like this. That now node 2 is on the queue. Moving ahead. We then check whether temp.right is equal to null or not. So here you can see temp.right is pointing to node 3, therefore it's not equal to null. So the condition in if block comes out to be true. And here we simply offer temp.right, which is the node 3 on the queue. So now node 3 is also on the queue. Moving ahead. Now in the while loop we check whether queue is empty or not. So currently queue has 2 nodes, therefore it's not empty. So the condition in while block comes out to be true. And then we simply pull an element from the queue and we'll assign it to temp node. So here you can see when we do a poll on the queue, the element which was inserted first would be the first to be removed. So therefore now 2 will be removed first and temp will point to the node 2. So it would look something like this. That node 2 is removed from the queue and its value will be assigned to the temp. So it means now temp is pointing to the node 2. Moving ahead. And then we will simply print the data associated with the temporary node, which is nothing but the 2. So 2 will be printed on the console. Moving ahead. And when we are visiting the node 2 of any particular level, then we have to add its left and right element on the queue. So here first we will check whether temp.left is equal to null or not. So currently temp.left is pointing to node 4, therefore it's not null. So the condition in if block comes out to be true. and then we will offer temp.left to the queue, which is nothing but the node 4. So now node 4 will be part of the queue. Moving ahead, and then we will check whether temp.right is equal to null or not. So temp.right is nothing but the node 5, and it's not equal to null. So the condition in if block comes out to be true, and we'll simply add the node 5 on the queue. Moving ahead, we again check whether queue is empty or not. So currently queue has 3 nodes, therefore it's not empty. So the condition in while block comes out to be true. And then we'll simply poll the element from the queue. So when we perform a poll operation, the element which was inserted first is first to be removed. So here you can see node 3 is the first element. So now it will be removed from the queue and its value will be assigned to the temporary node. So it would look something like this. So node 3 is removed and its value is assigned to the temporary node. So now temp is pointing to the node 3. Moving ahead, and then we'll simply print the data associated with the temporary node, which is nothing but 3. So 3 gets printed on the console. And then we'll simply check whether temp.left is equal to null or not. So here you can see temp.left is nothing but node 6, therefore it's not equal to null. So the condition in if block comes out to be true. And then we'll simply store the node 6 on the queue. Moving ahead, and then we'll check whether temp.right is equal to null or not. So here you can see temp.right is equal to null. So therefore the condition in if block comes out to be false, because we are not storing the null value on the queue. We again check whether queue is empty or not. So currently queue has 3 nodes, therefore it's not empty. And the first step, we simply poll the element from the queue and we'll assign it to the temporary node. So here node 4 will be removed from the queue and temp will now point to the node 4. So it would look something like this. So now temp is pointing to the node 4. And now we'll simply print the data associated with the temporary node, which is nothing but 4. So 4 will be printed on the console. And then we'll simply check whether temp left is equal to null or not. So temp left is equal to null, therefore the condition in if block comes out to be false. And we'll check whether temp right is equal to null or not. So temp right is also equal to null, therefore condition in if block comes out to be false. And then again in while loop we'll check whether queue is empty or not. So currently queue has 2 nodes, therefore it's not empty. So the condition of while block comes out to be true. And in the first step we'll simply poll the first element from the queue, which is nothing but node 5, and we will assign it to the temporary node. So it would look something like this. So now temp will point to the node 5. Moving ahead, then we'll simply print the data associated with the temporary node, which is nothing but 5. So now 5 will be printed on the console. Moving ahead, and then we will check whether temp left is equal to null or not. So currently you can see temp left is equal to null, therefore the condition in if block comes out to be false. And then we'll check whether temp right is equal to null or not. So here temp right is equal to null, therefore the condition in the if block comes out to be false. And then we go to while loop and we'll check whether queue is empty or not. So currently queue has 1 node left, therefore it's not empty. So the condition in while block comes out to be true. So we'll simply poll the element from the queue, which is nothing but the node 6, and we'll assign it to temporary node. So it would look something like this. So the node 6 is removed and now temp will point to the node 6. Moving ahead. So finally we will print the data associated with the temporary node, which is nothing but 6. So we have printed the data associated with the node 6. Moving ahead. We will check whether temp left is equal to null or not. So currently temp left is equal to null. Therefore the condition in if block comes out to be false. And then we'll check whether temp right is equal to null or not. So temp right is equal to null. Therefore the condition in if block comes out to be false. And finally we will again check whether queue is empty or not. So currently here you can see queue is empty. So therefore the condition in while block comes out to be false. Because queue is empty, so there are no more nodes left to be traversed. So therefore this while loop terminates. And we know that we have visited all the nodes of this binary tree level by level. So here you can see we first traversed node 1, then we visited node 2, then 3, then 4, then 5, then 6. So friend, this is the algorithm for the level order traversal of a binary tree. Now let's go to Eclipse and see its working code. So in this tutorial I will be coding the algorithm for level order traversal of a binary tree. So here I will be creating one method as public void, and I will give the name to its level order. So in this method we will be coding the level order traversal of a binary tree. So in the first step we'll check whether root is equal to null or not. So if root is equal to null, then we'll simply return from this method, because there are no nodes in the binary tree to be traversed. And then we'll initialize a queue which will hold the tree nodes for us. And here we are using the Java implementation of the queue. So we'll import it from the java.util package. So after we create the instance of this queue, we'll simply offer the root node. Now we'll create a while loop, and inside this while loop we'll place a condition as that we iterate this while loop till queue is empty. So inside this while loop we'll first create a tree node by name temp, and to this temporary node we'll poll the element from queue and we'll assign its value to the temporary node. And after polling the element from queue, we'll simply print its data on the console. So we'll do temp.data. So after printing the data associated with the temp node, we will store its left and right node on the queue. So we'll first check that whether temp left is equal to null or not. So if it is not equal to null, then we'll simply offer it to the queue. And similarly we'll do this for the temp right. So I will just copy it and I will make it to temp right. So friend, this is the algorithm for the level order traversal of a binary tree. Now let's test its working in the main method. So in the main method, we'll first create the instance of this binary tree class, and then we'll actually create the binary tree. So here you can see I have created this binary tree with the few nodes. So this is the binary tree which we discussed in the slide. And in order to know more about this create binary tree method, you can watch my previous tutorials. So after creating this binary tree, we will then call the method level order, and if I run the code now, so here you can see it printed 1, 2, 3, 4, 5, 6, 7, which we actually discussed in the slide, that it prints level by level. I hope you like this video. Please like, comment, share and subscribe my YouTube channel. Thanks, have a nice day.